Ultimately, knowledge and understanding of this long history of Earth open up prospects that can become the foundation for future generations. We all find ourselves on a journey through time and space on this amazing blue planet, which, despite its difficulties, continues to amaze us with its diversity and beauty. Every morning, when we wake up, we begin a new day in this magnificent cycle of life that has been going on for billions of years. The age of Earth represents a colossal and almost unimaginable scale of time, to which it is difficult to find parallels in our everyday perception. If we imagine Earth as an hourglass, the time that has passed since its formation stretches into infinity, while human life, including all of its history, is just a small handful of sand in one of those hours. Approximately 450 million years ago, the first complex organisms began to appear on the planet, and this is just a drop in the ocean of time that we call geological history. The evolution of life on Earth is something that has developed over millions of years, like a river flowing through mountains, creating canyons and depressions that we see today. Human life, as a spark in this vast flow, appeared only recently, if we compare it to the billions of years when Earth was just a cold sphere surrounded by clouds of dust and gas. Imagine that all events of human history, from the appearance of the first Homo sapiens to the present day, fit into a single moment when the river of time flows with power and unpredictability. Epochs such as the Stone Age, Bronze Age, and Antiquity seem like mere moments in the face of that grand chronicle, which includes events such as the formation of continents, mass extinctions, ice ages, and other geological catastrophes. For example, dinosaurs ruled Earth for more than 100 million years, their existence lasting longer than all of human history. When we look at the layers of Earth's crust that have formed over millions of years, we see the history of Earth as a book written with the help of volcanoes, oceans, and glaciers. Each layer is a separate chapter, telling us how the climate changed, how species changed, and how continents formed. Human achievements, such as the creation of the first cities, the invention of writing, and scientific discoveries, are just tiny points on a long line of time. For example, ancient Sumer, which began to develop around 5,000 years ago, is just one page in this vast book. While Earth has experienced billions of years, humanity has only become self-aware for a few thousand years, which challenges our perception of time. Consider how quickly we live. Days, months, and years fly by like a moment, and in the scale of Earth, this is just an instant. With each step on Earth, we are actually walking through history that spans millions of years. Each stone, each rock is a witness to ancient events that occurred long before humans appeared. For example, granite formed as a result of volcanic activity could be older than the earliest civilizations, and if it could speak, it would tell us about how Earth formed over millions of years. These historical layers resemble a multi-layered cake, where each layer is a unique period full of changes and transformations. Thus, if we try to grasp the scale of time that encompasses the entire history of Earth, it becomes clear that human life is just a small fragment in this boundless temporal continuum. This is like seeing one moment in a film that lasts several hours. And although we can recognize our significance, in the context of Earth, we exist only for a moment, like a flash of light that quickly fades. Each of our steps is just an echo in eternity, where time continues to flow like a river, never stopping and never looking back. Scientific research shows that Earth, as a planet, has a complex and multi-layered history, and we are only beginning to understand what happened over its long billions of years of existence. For example, some of the earliest forms of life appeared on Earth more than 3 billion years ago, when simple organisms began to inhabit the oceans. Since then, life has evolved, adapting to changing environmental conditions, leaving behind traces that scientists continue to study. These traces are not only fossils, but also changes in the composition of the atmosphere that indicate how life has influenced our planet. It is difficult not to be amazed at how life on Earth, despite all the catastrophes and changes, finds ways to survive and adapt. This is not only a history of struggle for existence, but also a history of cooperation and symbiosis that continues today. Each species, including humans, is the result of an endless process of changes that has passed through millions of years. We can only ponder how far this history extends and how it influences our perception of time and space. At the dawn of its existence, Earth was a molten sphere, covered by an ocean of magma with temperatures exceeding 1,000 degrees Celsius. The surface was unstable and constantly changing under the influence of volcanic activity. Volcanoes, like giant furnaces, ceaselessly spewed lava flows that shot into the sky, creating fiery rain that incinerated everything in their path. Each volcanic eruption was accompanied by a roar that echoed like thunder, reverberating across the entire sphere and creating an atmosphere of primeval chaos. In such moments, Earth could resemble a scene from a horror movie, with nothing but heat and fire, and the sky obscured by clouds of toxic gases. These gases, such as water vapor, carbon dioxide, and sulfur dioxide, created an opaque atmosphere that hid the fiery sea from space, leaving the planet in darkness. Scientists hypothesized that it was during this period, around 4 billion years ago, that Earth's crust began to form, slowly cooling and solidifying to create the first solid surface, which later became the foundation for continents. At this time, metals like gold and iron existed in liquid form, mixing with lava and forming a kind of cocktail that later emerged on the surface due to volcanic activity. This was a time of both destruction and creation. It was in these conditions that the first molecules, which would later become the basis for life, began to form. High temperatures and pressure facilitated the formation of mineral compounds, many of which became crucial for the formation of Earth's crust. Despite its hostility, this state of Earth served as a catalyst for future geological and biochemical processes. Volcanic activity led to the formation of new landforms, such as archipelagos and island chains, which greatly influenced the subsequent development of the planet. This period was as dynamic as the process of Earth's formation itself, with each volcanic eruption being a step towards the creation of the diverse landscapes we observe today. In this primeval heat and darkness, the first signs of what would one day make the planet a home for life began to emerge. In the cosmos, approximately 460 million years ago, the process of forming early Earth began from a cloud of cosmic dust and debris. These particles, primarily composed of hydrogen, helium, and heavy elements, were created as a result of supernova explosions and other cosmic phenomena. Under the influence of gravity, the particles began to slowly attract each other, forming clumps of matter known as planetesimals. These objects varied in size from centimeters to kilometers, and, upon colliding, formed increasingly larger bodies. During the period known as accretion, such collisions occurred millions of times, each event releasing colossal amounts of energy, leading to the heating of the material. As a result of intense heating, lighter elements such as hydrogen and helium rose to the surface, while heavier elements, including iron and nickel, began to sink towards the center of the forming object, creating a core that later became the basis for Earth's magnetic field. Approximately 30 million years after the start of accretion, protoplanets already existed on Earth, gradually increasing in size due to the continuation of collision processes. These collisions were so powerful that some resulted in the formation of craters similar to those observed on the Moon. Around 100 million years after the beginning of formation, one such impact became decisive. A collision with an object the size of Mars, known as Theia, resulted in the ejection of a massive amount of material into orbit, which later coalesced and formed the Moon. As a result of this catastrophic event, Earth continued to form, passing through stages of melting, where high temperatures led to the formation of magma, which gradually cooled, creating a solid crust. Over time, as the surface temperature decreased, conditions arose that favored the formation of the first oceans, which in turn led to the creation of an atmosphere primarily composed of carbon dioxide and water vapor. This initial stage of Earth's formation was crucial for the planet's further development, as it was during this period that the foundations for life were laid. By the time Earth had cooled and acquired its modern shape, more than 100 million years had passed since the start of accretion. During the formation of Earth, a natural process of differentiation occurred, which can be visualized as the separation of components in a molten mass. When the planet was in a molten state, various materials began to move depending on their density. Heavier substances such as iron and nickel gradually sank to the center, forming the core, while lighter elements such as silicon and aluminum rose to the surface, forming the mantle and crust. This process can be compared to the way oil and water separate when left alone. Oil, being less dense, always rises to the top, leaving water below. Thus, over the course of millions of years, the differentiation process resulted in a multi-layered structure of Earth, where each substance found its place under the sun. This separation took place over more than 100 million years. beginning approximately 4 billion years ago when Earth started to cool and form its modern structure. It is worth noting that this process created the conditions for the formation of tectonic plates, which later played a crucial role in the geological activity of the planet. As a result of differentiation, continents and oceans were formed, as well as the conditions necessary for the emergence of life. This complex interplay of densities, much like how vegetables are arranged in a salad by their weight, laid the foundation for future geological processes. Research shows that without this separation, Earth would not have been able to develop such dynamic systems as volcanism and earthquakes, which in turn influence the climate and ecosystems. This process, which occurred in the early days of our planet, determined its further development for billions of years to come. The formation of Earth's core began when the planet was still in a molten state. This process, lasting approximately 100 million years, was the result of gravitational forces that caused heavier elements such as iron and nickel to gradually sink towards the planet's center. Gravity acted like an invisible hand, attracting denser atoms that, through accretion, formed the core. Ultimately, under the immense pressure created by the layer of magma and other lighter elements, iron and nickel were compressed, forming a solid inner core and a liquid outer core. The pressure at the center of Earth reaches approximately 300 million atmospheres, equivalent to the pressure exerted by the weight of several planets above the core. This pressure endows metals with unique physical properties, allowing them to exist in a solid state even at incredible temperatures exceeding 6,000 degrees Celsius. The journey of heavy elements to the center took millions of years as they navigated through the molten mantle composed of less dense silicates and other minerals. These processes occurred under high temperature and pressure conditions, creating a dynamic environment where elements were constantly moving and redistributing. The liquid outer core plays a crucial role in generating Earth's magnetic field, while the solid inner core consists of crystalline structures formed over millions of years of compression and cooling. This unique core structure is the foundation for understanding the geodynamic processes occurring on our planet and helps explain many aspects of Earth's physics and geology. The formation of Earth's core was one of the most significant stages in its evolution, determining not only the planet's structure but also the conditions in which life on its surface developed. The mantle of Earth is a vast layer situated between the core and the crust, occupying approximately 93% of the planet's volume. This layer, extending to a depth of 2,900 kilometers, has a viscous, semi-liquid consistency, allowing it to behave as a flowing medium despite the immense pressure it experiences. Within the mantle, slow but powerful convective currents transport heat from the hot core to the Earth's surface. The temperature in the mantle ranges from about 1,000 to 4,000 degrees Celsius, making this ocean of molten rock incredibly active. These currents can move at a speed of just a few centimeters per year, but they are capable of causing significant geological changes on the planet's surface. For instance, the movements of the mantle are responsible for the formation of new mountain ranges and volcanoes, as seen in the region of the Pacific Ring of Fire. During these movements, the mantle interacts with the crust, creating various tectonic plates that can collide or diverge, resulting in earthquakes or the formation of new land features. At the heart of the mantle, processes can lead to the formation of magma, which subsequently erupts onto the surface through volcanoes. Each movement in the mantle can influence the climate and ecosystems, as changes in the positions of continents and oceans can lead to different climatic conditions that affect life on Earth. Therefore, the mantle, this colossal layer of molten rock under pressure, does not merely fill the space between the core and the crust, but actively participates in shaping the landscape and climate of our planet. The magnitude of the mantle, in combination with its dynamics, makes it one of the most important elements in the geological history of Earth. Approximately 4.5 billion years ago, when Earth was just beginning to form, one of the most catastrophic events in the history of our planet occurred. A collision with a protoplanet called Theia, the size of Mars. This collision, known as the Great Impact, became a turning point in the geological and astronomical history of Earth. The collision, which occurred at an enormous speed exceeding 20 kilometers per second, released a colossal amount of energy, equivalent to the explosion of millions of atomic bombs. As a result of this devastating impact, a portion of Earth's mantle, consisting of molten rock, was ejected into space, forming a cloud of hot gases and debris that orbited the young Earth. This cloud contained both heavy and light elements, and the temperature reached thousands of degrees Celsius, creating ideal conditions for the formation of new celestial bodies. Earth, already possessing gravity, began to attract these debris, which gradually coalesced into a disk around the planet. This disk consisted of particles that orbited Earth, colliding and combining with each other. Over millions of years, through a complex process of accretion, these debris began to form larger bodies, eventually transforming into our moon. According to scientists' estimates, this process took around 100 million years, resulting in the formation of the moon, which has a diameter of 3,480 kilometers and is approximately 1/4 the diameter of Earth. Thus, this collision not only led to the formation of the moon, but also altered the trajectory of Earth's development, affecting its axial tilt and, consequently, its climatic conditions. The moon, with its own gravity, played a significant role in stabilizing Earth's rotation, which in turn influenced the development of life on the planet. This event was catastrophic, but also creative, as without it, Earth might not have become the world we know today. Scientific research conducted using samples of lunar material collected during the Apollo missions confirms that the chemical composition of the Moon and Earth is very similar, providing additional evidence for the theory of their joint origin. The Moon is not just a satellite of Earth, it has become an integral part of our planetary system, influencing numerous processes that shape the conditions for life. Its presence over approximately 4.5 billion years has created unique conditions that cannot be underestimated. The Moon stabilizes Earth's axis of rotation, which in turn affects climatic conditions and leads to the creation of diverse ecosystems. Without the Moon, the angle of Earth's axis could have fluctuated much more significantly, making the climate more extreme and unpredictable. These fluctuations could have resulted in sharp temperature changes, ultimately hindering the development of life as we know it. The Moon also governs tides and ebbs, creating dynamic aquatic ecosystems. For instance, tides caused by the Moon's gravitational influence help mix water in the oceans, providing oxygen to marine organisms and facilitating their reproduction. Such conditions are vital for supporting marine flora and fauna, including coral reefs, which are key elements of marine ecosystems. Furthermore, the interaction between the Moon and Earth creates gravitational forces that contribute to the stability of atmospheric pressure and the formation of weather systems. This influence dates back to ancient times when the Moon was just beginning to form, and since then, the relationship between Earth and its satellite has only grown stronger. The Moon has also become a symbol for many cultures, inspiring mythology and science. To the ancient Sumerians, the Moon was associated with the god Nana, embodying wisdom and time. In ancient Egypt, the lunar calendar was used to determine the timing of agricultural work, underscoring its importance for the development of civilization. Even in the modern world, the influence of the Moon is felt in the rhythms of life of many species, including humans. Studies have shown that lunar phases can affect behavior, including sleep cycles. The Moon continues to be a subject of scientific research and cultural interest, as its influence on Earth remains significant to this day. Every night, we observe its light, which reflects solar rays, creating unique nightscapes and influencing our perception of time and space. Scientific missions like Apollo have confirmed that the Moon is not just a lifeless rock, but an active participant in Earth's history, and its influence is felt in many aspects of life. Although we still do not fully understand all the mechanisms of interaction between Earth and the Moon, one thing is clear. Without this massive satellite, our world would be completely different, and many biological and geological processes could have unfolded in entirely different ways. The presence of the Moon has become the foundation for the formation not only of physical, but also of cultural aspects of life on our planet. The Moon exerts a significant influence on the tides of the Earth's oceans, a process that can be observed daily. The gravitational pull of the Moon attracts ocean waters, causing them to rise and form tidal waves that twice a day wash the shores. Tides and ebbs occur approximately every 6 hours, creating a unique rhythm in the lives of coastal ecosystems. The most impressive tides are observed in places like the Bay of Fundy in Canada, where the difference between high and low tide can reach 26 meters. These constant water movements shape coastal lines, creating unique landscapes such as estuaries and shallow bays. In their work, tides and ebbs contribute to the erosion of coasts and the formation of new islands. as well as providing suitable conditions for the life of numerous marine organisms. Tidal zones formed by these movements are among the most productive ecosystems on Earth, where mollusks, crabs, fish, and many other species adapted to changing conditions live. In ancient times, when the moon was closer to Earth, tides were even more powerful, creating enormous tidal waves that swept onto continents, significantly influencing climate and ecosystems. Scientists estimate that the distance between the moon and Earth has increased by about 3.5 centimeters per year over the past millions of years, leading to a decrease in tidal strength. These changes not only affect the water level, but also the migration of marine animals such as turtles, which use tides to access feeding grounds and breeding sites. The diversity of life in tidal zones depends on the time of day and the phase of the moon, making the observation of these processes particularly interesting for scientists and nature enthusiasts. These cyclic changes also affect human activities, from fishing to recreation, and shape cultural traditions related to the sea. Each tide and ebb serves as a reminder of how closely all aspects of life on Earth are interconnected, and how the moon, located more than 380,000 kilometers away, continues to influence our world. The moon plays a pivotal role in stabilizing Earth's axis, maintaining the planet's axial tilt within a range of 22 to 26 degrees. This may seem insignificant, but this small angle is critically important for maintaining Earth's climatic stability. Due to its massive mass, which is approximately 1/8 of Earth's mass, the moon acts as a giant anchor, preventing chaotic oscillations of the planet's rotational axis. This stabilization mechanism has been studied by many astronomers, including the famous scientist Copernicus in the 16th century, and the modern astronomer Brian Maynard, who in 2006 confirmed that without the moon, Earth's axial tilt could fluctuate by more than 10 degrees in either direction. This would have led to catastrophic climate changes, such as sudden temperature shifts and more extreme seasons, making the development of complex life forms extremely difficult or even impossible. Research shows that such axial oscillations could have caused ice ages to occur and disappear much more frequently than they do now, making ecosystems less resilient. Additionally, the stability of the axial tilt influences the distribution of solar light across the planet's surface, creating diverse climatic zones from the tropics to polar regions. The existence of numerous species, from diverse tropical plants to polar bears, depends on this climatic stability provided by the moon. If Earth were to rotate without this stable satellite, the climate could change on such a scale that ecosystems would not have time to adapt to the new conditions, and many species would likely go extinct. The moon, located at a distance of more than 380,000 kilometers, does not just illuminate the night sky, but also actively shapes the conditions for life on the planet, acting like an invisible master, controlling the balance of the entire system. For example, according to astronomers' calculations, if Earth had no moon, its axis could tilt up to 60 degrees, resulting in catastrophic consequences for all living nature. Ancient civilizations intuitively recognized this connection, as evidenced by numerous myths about the moon, where its image is often associated with life and stability. Therefore, the influence of the moon on Earth's climate and ecosystems is much deeper than it might initially appear. In the early stages of Earth's formation, the planet was in a state of complete liquefaction, like a vast bowl of boiling metal. The internal layers were saturated with hot minerals and elements that sought equilibrium. Gradually, as it cooled, heat began to dissipate slowly into the boundless cosmic space, like steam from a hot soup that cools, forming a thin film on the surface. This was a process that could not be observed instantaneously. It took millions of years for the upper layers of Earth to begin to solidify. Initially, a thin crust formed, resembling the film that appears on the surface of hot milk as it cools. This crust served as the first protective layer against cosmic influences, but beneath it, volcanic activities still raged. With each new million years of cooling, the crust thickened, its structure changed, and the first continents began to form. During this period, volcanic eruptions pushed new layers of magma to the surface, which, as they cooled, transformed into basalt, creating the landscape that would later become the foundation for land. Other minerals, such as granite, also formed, which would later become the main part of the continents. Water contained in the gases released from the interior gradually condensed, forming oceans. This was not just a process of cooling, but a true transformation that prepared the ground for further life development. Gradually, Earth transitioned from a molten state to a solid surface, where over billions of years, conditions arose that allowed the emergence of the first forms of life. This transition from a hot, unstable state to a cooler and more stable one was fundamental for the formation of the planetary ecosystem and the appearance of an atmosphere that protected Earth from harmful cosmic rays. Ultimately, the formed continents and oceans became the basis for future ecosystems that would later be inhabited by numerous forms of life. The cooling of Earth, like the melting and solidification of metal, became the foundation for all the geological changes that occurred in subsequent epochs. On the surface of the molten ocean of magma, which formed as a result of intense volcanic activity and collisions of planetesimals, the first solid areas began to appear, forming the primary crust of Earth. These areas, which were thin and fragile crusts, emerged around 4 billion years ago when the surface temperature dropped to a level that allowed the magma to solidify. The first islands of solid rock, only a few centimeters thick, floated on the surface of the liquid rock, like tiny plates drifting on vast seas. These crusts were constantly being destroyed by the internal forces of the planet. Tectonic movements, caused by convection currents in the mantle, collided with these primary formations, destroying them and creating new structures. As a result, new crustal areas formed during collisions, which were then also subjected to destruction. This was an endless cycle of creation and destruction, reminiscent of a game of ping-pong, where each hit could lead to instant destruction. The density of the primary crust was significantly lower than that of modern continents, making it unstable and prone to deformation. These first islands did not have clear boundaries and were not connected to each other, forming scattered areas that were unlike modern continents. They were subject to erosion and destruction, as well as the formation of new solid rocks through the crystallization of magma. During this destruction, gases such as water vapor and carbon dioxide were released, gradually forming the primary atmosphere and creating conditions for further life development. These primary crusts, only a few tens of meters thick, were no more than temporary formations. Over time, under the influence of internal processes, many of them sank back into the magma, where they again became liquid, continuing the cycle. As a result of this chaos, new crustal areas continued to form on the surface of Earth, which, although fragile, marked the beginning of the long path of our planet's formation. It is important to note that the early crust was far from the strength and stability of modern continents, such as the Eurasian or North American plate, which formed millions of years later. The early Earth's atmosphere was a dense, opaque shroud composed of toxic gases that enveloped the planet like a deadly veil. During the period from 4.5 to 3 billion years ago, as the Earth was just beginning to form, massive volcanic eruptions filled the air with carbon dioxide, sulfur dioxide, and other poisonous compounds. For instance, volcanoes similar to those currently found in Hawaii would spew lava and smoke into the atmosphere, creating a terrifying landscape. Evaporation from the scorching surface, which reached temperatures above 1,000 degrees Celsius, formed thick clouds that trapped heat but blocked out sunlight. This resulted in the planet being shrouded in eternal twilight, where darkness and despair reigned. In such an atmosphere, free oxygen was absent, as its sources, the photosynthetic organisms, had not yet emerged. The oxygen level in the atmosphere remained extremely low, making it completely inhospitable to modern forms of life. Sulfur dioxide, released during the breakdown of organic matter, created a distinctive odor of rotten eggs and added further toxicity to the atmosphere. Such a composition of gases could have killed any familiar form of life in mere minutes. Nevertheless, in this lifeless and hostile world, important chemical reactions were taking place that could ultimately lead to the emergence of the first simple organisms. These conditions, though deadly for most modern forms of life, laid the foundation for further evolutionary processes. An atmosphere rich in methane, ammonia, and other gases created unique conditions for the formation of the first molecules capable of self-replication. Eventually, such molecules became the precursors of life that would appear billions of years later. Scientific research indicates that around 3.5 billion years ago, the first prokaryotes began to emerge, marking a significant event in the history of Earth. The process of degassing Earth, which lasted millions of years, was a crucial stage in the formation of its atmosphere. Within the planet, primarily in the mantle, gases such as carbon dioxide, water vapor and methane accumulated. These gases were under high pressure and temperature, and at some point, the forces acting on the planet began to release them. Volcanic eruptions, occurring in various parts of the Earth, became the main exits for these gases to the surface. Volcanoes, like the planet's giant respiratory tracts, exhaled their internal atmosphere through their craters, releasing clouds of steam and gas. This process occurred over long periods, resulting in the formation of new layers of the Earth and changes in the structure of the crust. For example, during a major volcanic eruption that occurred around 200 million years ago, a vast amount of carbon dioxide was released into the atmosphere, altering its composition and climate. Often, volcanoes formed extensive lava fields and cinder cones, which served not only as sources of gases, but also shaped the landscape. With each new burst of activity, the planet exhaled more gases, creating conditions for the formation of a more stable atmosphere. Gradually, through numerous eruptions and fractures in the crust, a gaseous envelope was formed, which became the basis for further development of life on Earth. This process of degassing was not a one-time event, but rather a continuous cycle, where each burst of activity contributed to atmospheric changes that ultimately influenced climatic conditions and the evolution of living organisms. The gases released by volcanoes constantly mixed with atmospheric components, creating conditions favorable for the formation of clouds and ultimately precipitation. Similar processes are observed today when active volcanoes continue to exhale gases, maintaining the dynamics of the atmosphere. For example, the Kilauea volcano on Hawaii, which has been actively erupting since the late 18th century, releases significant amounts of sulfur gas into the atmosphere, affecting the local climate and ecosystem. The formation of the atmosphere was the result of long-term volcanic processes that provided the world with unique conditions for further development of life. In the first billion years after the formation of Earth, when the planet was in a state of high temperatures and active volcanism, the atmosphere consisted mainly of water vapor, carbon dioxide, and ammonia. As Earth gradually cooled, the temperature in the atmosphere began to decrease, leading to the condensation of water vapor. This process began approximately 3.5 billion years ago when the surface temperature of the planet fell to 100 degrees Celsius. As a result, water vapor began to transform into droplets of water, which gradually formed clouds. The continuous cooling of the planet caused endless torrential rains that poured down for millions of years. These rains were like streams that crashed onto the surface with such force that they formed rivers and lakes in lowlands and depressions, filling them to the brim. Around 3 billion years ago, when the accumulated water began to collect, the first seas were formed. As the rainy activity continued, the tectonic plates began to rise and fall, creating relief that facilitated the formation of oceans. Approximately 2.5 billion years ago, when the water level reached significant proportions, seas and oceans began to occupy a large part of the Earth's surface. The formation of oceans was a significant milestone in Earth's history, as it was in these waters that processes began that led to the emergence of life. The scale of this deluge is difficult to imagine. According to some estimates, over billions of years, more than 30 million cubic kilometers of water fell on Earth, enough to fill an ocean with a depth of tens of kilometers. These primeval oceans became the habitat for the first microorganisms, which in turn began to alter the atmosphere by releasing oxygen through photosynthesis, ultimately leading to the formation of the modern climate. That very process of water vapor condensation and its transformation into oceans became the foundation for the further evolution of the planet and its ecosystems, creating conditions for the existence of various forms of life that we know today. The early ocean of Earth was a colossal chemical laboratory filled with minerals and organic compounds washed out of rocks and brought by meteorites. Around 4 billion years ago, this vast water mass reached temperatures of about 100 degrees Celsius, facilitating high levels of evaporation and cloud formation. Yet the water surface was rich in various elements. The water in this ocean had an acidic reaction, with a pH ranging from 3 to 6, which was significantly different from the neutral reaction of modern seas. In addition to the basic elements like hydrogen and oxygen, the water contained a large amount of dissolved minerals, sulfates, carbonates, chlorides, and even heavy metals such as nickel and cobalt. These substances entered the ocean through volcanic eruptions and leaching from the Earth's crust. Over time, the ocean became filled with organic molecules that formed as a result of chemical reactions between simple compounds. For instance, a process known as abiogenic synthesis allowed the formation of amino acids, which became the foundation for the first proteins. The ocean of that time also had a characteristic color, ranging from orange to greenish, due to the presence of iron oxides and other metals. The smells emanating from this primeval sea were more chemical than the familiar marine aromas. It was not freshness, but rather the smell of hydrogen sulfide and ammonia, creating an atmosphere filled with mysteries and dangers. The consistency of the water varied from thick and viscous to almost transparent, depending on the concentration of dissolved substances. The ocean had no inhabited islands, only vast empty spaces interrupted by rare volcanoes that spewed new rocks and minerals into the water. This unique environment fostered numerous chemical reactions that ultimately became the basis for the emergence of the first living organisms. Each of these reactions in the ocean could last for millions of years, creating conditions for the evolution of life on Earth. For example, during this period, simple cells consisting of lipid membranes could have formed, which began to aggregate into capsules capable of self-replication. Thus, the early ocean was not just a body of water, but a true laboratory where countless processes took place that ultimately prepared the ground for the appearance of life. The composition of the early ocean, its high temperature, acidity, and unique chemical reactions defined not only its character, but also the future of the entire planet. Primary soup is a concept describing the oceans of Earth in deep antiquity, when they contained a rich mixture of substances necessary for the emergence of life. These oceans likely contained amino acids, carbohydrates, and other organic molecules that formed as a result of various natural processes. The water in these primordial bodies acted as a solvent, allowing chemical substances to interact and form more complex structures. This environment resembled a kind of nutritious broth, where, like in a culinary recipe, all the ingredients were present for the creation of the first living organisms. Energy from various sources played a crucial role in transforming simple chemical compounds into more complex molecules. For instance, lightning, with its high temperatures and pressures, facilitated chemical reactions. Ultraviolet radiation from the sun could also initiate these processes, affecting molecules in the ocean and triggering complex photochemical reactions. Another important energy source was hydrothermal vents, which released hot water and minerals from the Earth's interior onto the ocean floor. These sources created unique conditions for the formation of life, as temperatures in such places could reach hundreds of degrees Celsius. Research shows that such zones are home to ecosystems based on chemosynthesis, where organisms obtain energy not from sunlight but from chemical reactions. These conditions provided an ideal environment for the interaction of chemical substances, which contributed to the formation of the first cells. The appearance of such cells became possible due to the accumulation of molecules that could self-replicate and evolve, ultimately leading to the diversity of living organisms we observe today. Scientific models, such as the primary soup hypothesis, emphasize the importance of these early oceans as the cradle of life on the planet. Research indicates that it was in such energy-rich and chemically laden conditions that life on Earth could have originated. Hydrothermal sources on the floor of an ancient ocean represent incredible underwater oases, where hot mineral-rich waters are expelled from cracks in the ocean floor. These sources are often referred to as black smokers, due to the clouds of black mineralized sediment that form when hot water interacts with cold seawater. The temperature of the water in these sources can exceed 250 degrees Celsius, and the pressure at depths of around 2,000 meters can reach 100 atmospheres. These conditions create a unique environment where organisms capable of surviving in extreme conditions thrive. For example, at deep-sea hydrothermal vents in the mid-ocean ridges, such as the mid-ocean ridge, bacteria have been found that obtain energy from the oxidation of hydrogen sulfide released from the vents. These organisms, such as archaea and sulfur bacteria, form the basis of the ecosystem around hydrothermal vents, creating a food chain that includes various marine organisms, including mollusks and crustaceans. These places are not only biological, but also geological phenomena, where temperature and the concentration of various substances change dramatically. Around these sources, mineral deposits such as spheres of sulfur and ice of minerals form, creating breathtaking underwater landscapes. Using deep-sea submersibles like Alvin, Researchers, including the Woods Hole team, have discovered numerous such sources since the mid-20th century, opening new horizons for understanding the origin of life on Earth. It is here, in these underwater hot springs, that many scientists believe life could have originated, as they provide the necessary elements and conditions not found in other parts of the ocean. These sources not only demonstrate how organisms can exist in extreme conditions, but also offer the possibility of understanding how life could have arisen on other planets with similar conditions. Located at depths of more than 3,000 meters, these oases are true wonders of nature that continue to attract the attention of scientists and researchers from around the world. In recent years, studies have been conducted to investigate the microorganisms living in such conditions, which supports the hypothesis that life on Earth could have begun in such places. In the oceans that formed more than 3 billion years ago, the process of forming the first organic molecules began, which served as the foundation for the emergence of life. Water containing dissolved gases such as methane, ammonia, and water vapor created ideal conditions for chemical reactions. These gases, in turn, interacted with solar light and electrical discharges, forming more complex compounds. In the 1950s, Stanley Miller and Harold Urey conducted a famous experiment, known as the Miller-Urey experiment, in which they recreated conditions similar to those that existed on early Earth. As a result of these reactions, amino acids were obtained, which are the building blocks of proteins. This experiment demonstrated that simple molecules, under the influence of energy, could evolve into more complex structures. Gradually, as a result of numerous chemical reactions, molecules capable of self-organization began to form. For example, some lipids interacting with water formed micelles, structures resembling cell membranes. This was the first step towards the formation of more stable molecular complexes that could later perform functions necessary for life. During these processes, organic molecules began to exhibit properties that allowed them to interact with each other, forming more complex compounds. Complex molecules, such as ribonucleic acid, RNA, became possible due to the sequential accumulation of chemical complexity. In 1983, Francis Crick, a biochemist, proposed the hypothesis that RNA could serve not only as an information carrier, but also as a catalyst, facilitating chemical reactions. At this stage, molecules began to exhibit the ability to self-replicate, which was critically important for the formation of the first simplest forms of life. In such conditions as high temperatures and various chemical environments, protocells arose, which could preserve and transmit genetic information. As a result of natural selection, molecules that better adapted to their conditions of existence emerged, ultimately leading to the appearance of the first single-celled organisms. These processes took place over millions of years, resulting in the formation of the foundations of biochemistry, which became the basis for life on Earth. 80% of the modern oxygen in the atmosphere comes from photosynthetic bacteria, which evolved from these first organisms. The study of self-replicating molecules opens up a fascinating world of chemical evolution. These molecules, akin to seeds, possessed a unique ability to create copies of themselves, utilizing available elements and compounds from their surroundings. This process occurred through chemical reactions in which molecules combined and shared their structure, transforming inorganic substances into something more complex. Once they appeared, such molecules began to spread, like seeds carried by the wind, and evolve, adapting to various conditions. The significance of self-replicating molecules lies in the fact that they became the cornerstone of the transition from simple chemical reactions to more complex biological processes. The emergence of such structures can be seen as a moment when uncontrolled chemical reactions began to organize into more predictable and stable forms of life. For instance, in the early Earth's environment, rich in chemical substances, self-replicating molecules could have arisen in hot springs or near ocean shores, where temperature and chemical conditions favored their formation. Such molecular replication was not merely a coincidence, but a result of complex interactions occurring at the microscopic level. It is important to note that self-replicating molecules were not static. They changed and adapted, passing through numerous generations, allowing them to survive and develop. This process of molecular-level evolution laid the foundation for the appearance of the first cells, which possessed more complex replication mechanisms. Self-replicating molecules represent a crucial step in the evolutionary chain, as they initiated what later became biological life. Contemporary research indicates that such molecules likely emerged more than 3 billion years ago, during a time when Earth was young and full of chemical possibilities. For example, in some laboratory experiments, scientists have been able to recreate conditions under which molecules similar to RNA could self-replicate, thereby supporting the theory that life may have begun with such structures. These experiments highlight the crucial role of self-replicating molecules in the history of life on Earth, as they formed the basis for all the living organisms we know today. The formation of the first cellular membranes was a crucial stage in the development of life on Earth. About 4 billion years ago, when the conditions on the planet were far from today's, certain molecules, such as phospholipids, began to aggregate into thin films. These molecules have hydrophilic heads that seek to interact with water and hydrophobic tails that conversely avoid moisture. As a result of their combination, primitive structures resembling bubbles were formed, which could separate the internal contents from the external environment. These bubbles, or liposomes, created a protected space in which chemical reactions necessary for the emergence of life could occur. These membranes were not static. They could grow, divide, and fuse with other bubbles, creating increasingly complex structures. This process, known as membrane dynamics, allowed the formation of miniature cells that could effectively concentrate chemical reactions in a limited space. This significant simplification of conditions for chemical processes occurring inside membranes accelerated evolutionary processes, as it increased the likelihood of the emergence of new molecules capable of self-replication. In such conditions, where molecules could interact more effectively, new evolutionary possibilities arose. It is important to note that the presence of membranes was fundamental to the formation of the first primitive cells, which later evolved into more complex organisms. These early cellular structures were predecessors of all modern cells, from bacteria to plants and animals. Thus, cellular membranes not only protected the contents, but also played a decisive role in the evolution of life, allowing the creation and maintenance of complex chemical processes. A significant aspect is that membranes provided isolation and protection from adverse external factors such as ultraviolet radiation and high temperatures, allowing emerging life to adapt and develop in conditions that would be destructive without this protection. Scientific research conducted in the 20th century confirmed that such simple membranes could serve as the basis for the formation of the first cells, and experiments with phospholipids demonstrated how they spontaneously form structures similar to cellular membranes. In particular, in the early 2000s, scientists such as David D. Drexler conducted experiments showing that even in simple solutions, phospholipids can spontaneously self-organize, forming stable membrane structures. These discoveries open new horizons in understanding the evolution of life and show how simple molecules became the basis for complex biological systems. For example, in the early 2000s, a team of scientists from MIT, under the leadership of Professor Stephen R. Kotler, conducted several experiments showing how membranes can change their shape and properties depending on the surrounding environment, further emphasizing their dynamic nature. First prokaryotic cells, which emerged around 3.5 billion years ago, became the foundation of life on Earth. These primitive single-celled organisms, ranging in size from 1 to 10 micrometers, lacked a nucleus and complex organs, making them much simpler compared to modern cells. The walls of these cells consisted of lipids and proteins, while their internal structure was a gel-like substance known as cytoplasm, which contained ribosomes for protein synthesis. Prokaryotes could utilize various energy sources. Photosynthetic types, such as cyanobacteria, captured sunlight, while others, like methanogens, used chemical reactions to obtain energy from inorganic compounds. These organisms grew by absorbing nutrients from their surroundings, such as simple sugars and amino acids, which entered the cell through the cell membrane via diffusion and active transport. Prokaryotes reproduced through a process called binary fission, in which the cell doubled and then split into two identical daughter cells, allowing for rapid population growth. In the ancient ocean filled with toxic substances and variable conditions, prokaryotes demonstrated remarkable resilience. They could survive in extreme temperatures, high salt levels, and even acidic conditions, allowing them to colonize the most diverse niches on Earth. One striking example is the existence of thermophilic bacteria that inhabited hot springs where temperatures exceeded 80 degrees Celsius. These organisms not only survived but thrived, demonstrating remarkable adaptive mechanisms. It is important to note that prokaryotes became the primary producers of oxygen on the planet through photosynthetic processes, which in turn led to significant changes in the atmosphere and allowed for the evolution of more complex life forms. These ancient organisms laid the foundation for the future biosphere, demonstrating that simplicity can be the key to survival in complex conditions. Prokaryotes, as living witnesses of their time, remain an integral part of modern ecosystems, continuing to perform vital functions in the biosphere, such as the decomposition of organic matter and nitrogen fixation. Stromatolites are layered structures created by colonies of microorganisms, which are among the oldest evidence of life on Earth. These structures form due to bacterial mats that capture and consolidate sedimentary particles, creating characteristic domes and columns. The formation process of stromatolites resembles a construction process, where each new layer is added to the existing ones, resulting in unique geological formations. These formations grow extremely slowly, sometimes over thousands of years, allowing them to accumulate information about climate and environmental conditions over different historical epochs. For example, in conditions of calm water and the absence of strong currents, microbial colonies can develop more actively, forming thicker layers. Conversely, in conditions of increased water agitation or changes in the chemical composition, their growth can significantly slow down. Stromatolites serve as a kind of chronicles of geological time, reflecting the passage of time like the annual rings of trees. Each layer can testify to various living conditions and ecosystems in which the microorganisms existed, from warm, shallow lagoons to more harsh conditions. These structures also demonstrate how life on Earth has adapted to changing conditions. From the oxygen catastrophe, when the level of oxygen in the atmosphere began to increase, to its subsequent impact on ecosystems. Stromatolites have not only geological but also biological significance, as they help scientists better understand the origin of life on Earth and its evolution. They are the only living fossils that can be observed and studied today, providing a unique opportunity to look into the distant past. Colonies of cyanobacteria that form these structures are predecessors of modern plants, highlighting their importance in the history of life on the planet. Stromatolites can reach significant sizes, sometimes exceeding 2 meters in height, indicating a multi-century process of their formation. These structures demonstrate how simple organisms can create complex ecosystems and influence geological processes. Stromatolites are known for their ability to photosynthesize, which also played a key role in changing the Earth's atmosphere in ancient times, preparing conditions for the emergence of multicellular life. Research on stromatolites continues to open new horizons in understanding how life can survive and adapt to the most diverse conditions. They remain a bright testimony to how life on Earth has developed over billions of years, shaping the world we know today. Stromatolites are at the center of many studies, allowing scientists to make conclusions about climatic changes and biological evolution throughout geological history. Shark Bay in Australia is a unique place where stromatolites, colonies of microbial organisms, thrive. These structures, often referred to as living fossils, have been preserved since the earliest times. They are formed by the actions of cyanobacteria, which create layers of limestone by depositing minerals around themselves. In this shallow, high-salinity bay, where the depth rarely exceeds 2 meters, the clear water reveals rounded domes and columns formed billions of years ago. The stromatolites in Shark Bay are among the oldest in the world, with an age of up to 3 billion years. These ancient formations grow slowly, adding less than 1 millimeter per year, making them challenging to study for scientists, but also providing a window into the distant past of our planet. Their shape and structure resemble those that existed during the Archean era, when life was just beginning to colonize Earth. By studying these colonies, scientists can reconstruct the conditions of ancient oceans by analyzing the composition of the sedimentary rocks surrounding the stromatolites and the chemical elements they contain. In Shark Bay, one can observe how stromatolites form complex ecosystems, inhabited by a variety of marine organisms, from mollusks to small fish. This allows scientists to not only study the biological aspects of ancient life, but also understand how ecosystems have adapted to changing environmental conditions over millions of years. Stromatolites in Shark Bay attract the attention of not only scientists, but also tourists eager to see these unique formations, which are significant for understanding the evolution of life on Earth. In the 21st century, Shark Bay was inscribed on the UNESCO World Heritage List due to its unique natural features and scientific significance. Scientists like Professor Hayden Bennett from the University of Western Australia conduct research aimed at understanding how stromatolites can contribute to the study of climate changes and potential ecosystems that could exist on other planets. This place has become a kind of laboratory for studying the evolution and adaptation of life, allowing us to better understand how life on Earth can survive in conditions that would be considered extreme for most modern forms of life. Stromatolites in Shark Bay continue to be an important object of research as they demonstrate how life can survive and thrive in conditions that would be difficult to comprehend from a modern perspective. These living fossils not only tell the story of a distant past, but also open new horizons for scientific discovery. Photosynthesis is one of the most remarkable processes on Earth, occurring more than 3 billion years ago. It was a true revolution in the life of our planet, enabling organisms to catch sunlight and convert it into chemical energy. As a result of this process, living beings were able to use solar energy to create nutrients from simple compounds like carbon dioxide and water. This is not just the conversion of light into food. It is a fundamental shift in the way energy is obtained. The first organisms to master photosynthesis began to release oxygen into the atmosphere, marking a catastrophic turn in the planet's history. The oxygen they produced accumulated in the atmosphere, causing changes that ultimately led to the emergence of various forms of life, including animals and humans. This process not only altered the composition of the atmosphere, but also laid the foundation for complex ecosystems. Before the advent of photosynthetic organisms, Earth's atmosphere was extremely low in oxygen, and life existed in conditions far removed from our modern notions of comfort. With the advent of photosynthesis, something extraordinary happened. The planet began to breathe. The evolution of photosynthetic organisms led to the creation of diverse forms of life, each of which, in turn, depended on the oxygen produced by these first sun catchers. This process became the basis for food chains that we observe today. Plants, algae, and even some bacteria became the primary producers in ecosystems, providing nutrients and oxygen for other forms of life. Thus, photosynthesis not only changed the atmosphere, but also created conditions for a complex biosphere. Without this process, life in its current form would be impossible. Photosynthesis is not just a method of obtaining energy. It is the key to understanding how life on Earth can survive and evolve in conditions that were once deemed inhospitable. It is one of the most significant evolutionary breakthroughs that has ever occurred on our planet, opening the way to the diversity of life forms we know today. Scientific research shows that photosynthesis has become the basis for the formation of the carbon cycle, which regulates the climate on Earth. Scientists continue to explore how photosynthesis can be used in modern technologies, for example, to create sustainable energy sources. Ultimately, photosynthesis is not just a process. It is the foundation of all life on our planet. The existence of photosynthetic organisms has become one of the cornerstones of the ecosystems we observe today. Cyanobacteria, also known as blue-green algae, appeared on Earth more than 3 billion years ago and became the first organisms to use sunlight for photosynthesis. These microorganisms have the unique ability to convert carbon dioxide and water into organic compounds, simultaneously releasing oxygen as a byproduct. They formed extensive colonies that colored the shallow waters of ancient oceans in vibrant blue-green hues, creating true biological landscapes. These colonies were so large that they could significantly affect the color of water bodies, leading to their occasional description as blooming waters. Cyanobacteria used various adaptations to survive in different conditions, from deep seas to saline lakes, and possessed the ability to form cysts, protective structures that allowed them to survive in unfavorable conditions. Over millions of years, these bacteria not only provided themselves with energy, but also created conditions for the survival of other organisms. Through photosynthesis, cyanobacteria altered the composition of Earth's atmosphere, increasing the level of oxygen to critical values necessary for the emergence of aerobic life. Around 2 billion years ago, an event known as the oxygen catastrophe occurred, when the level of oxygen in the atmosphere significantly increased, leading to massive changes in ecosystems and the evolution of various forms of life. This oxygen became the basis for multicellular organisms, including plants and animals. Cyanobacteria, with their ability to photosynthesize, became key players in this process, providing oxygen to the planet and creating conditions for the complex ecosystem that exists today. Their impact on the biosphere is immeasurable, as they were the predecessors of all photosynthetic organisms, including higher plants that we observe today. Research shows that cyanobacteria continue to play a crucial role in modern ecosystems, participating in the carbon and nitrogen cycles and in oxygen production, which underscores their significance in the history of life on Earth. The ability of cyanobacteria to photosynthesize has laid the foundation for many studies in ecology and biotechnology, as scientists strive to use them to develop new sustainable sources of energy. Oxygen catastrophe, a concept describing a dramatic change in the chemistry of the atmosphere and oceans that occurred as a result of the accumulation of oxygen produced by cyanobacteria. While cyanobacteria began to actively photosynthesize, they released oxygen into the atmosphere, altering its composition and creating conditions that were catastrophic for most organisms that inhabited the Earth. These organisms, including anaerobic bacteria and protozoa, had evolved in an oxygen-free environment and could not adapt to the rapidly changing conditions. Oxygen, which is now considered essential for the survival of most living beings, was at that time a true poison. The accumulation of oxygen led to a mass extinction event known as the Great Dying, during which many forms of life that could not survive in the newly oxygenated environment perished. For example, anaerobic bacteria, which lacked protective mechanisms against oxidative processes, died in enormous numbers. The paradox of this situation is that the substance which became fundamental for breathing and the existence of modern organisms was the cause of the demise of previously dominant life forms on the planet. As the concentration of oxygen in the atmosphere increased, changes also occurred in the oceans, where the level of dissolved oxygen also increased, leading to significant changes in ecosystems. As a result of this process, new organisms capable of surviving in an oxygenated environment emerged, such as aerobic bacteria and subsequently multicellular organisms. This laid the foundation for the evolution of more complex forms of life, including animals and plants, which we observe today. The oxygen catastrophe also initiated oxidative processes that influenced geochemical cycles and the formation of the atmosphere. Scientific research shows that the level of oxygen in the atmosphere at that time reached up to 21%, which is significantly higher than the current level. This change in the chemical composition of the atmosphere had a profound impact on the climatic conditions and ecosystems on Earth, contributing to the emergence of new ecosystems and the transformation of existing ones. Thus, oxygen became not only a source of life, but also a catalyst for mass extinction, highlighting the complexity and contradiction of evolutionary processes on our planet. Scientific research shows that for many organisms to adapt to the oxygenated environment, millions of years of evolution were required, leading to the formation of new ecosystems. Complex organisms such as fish and terrestrial animals emerged as a result of these changes, opening a new era in the history of life on Earth. The oxygen catastrophe was a pivotal moment in the history of Earth, altering the course of evolution and making possible the existence of the modern biodiversity we see today. During the oxygen catastrophe, which occurred approximately 2.5 billion years ago, massive oxidation of dissolved iron began in the oceans. In ancient seas rich in iron, a chemical reaction occurred when free oxygen produced by cyanobacteria interacted with dissolved iron ions. This process led to the formation of iron oxides, which gradually settled on the ocean floor as sediment. These sediments, primarily composed of hematite and other iron-containing minerals, formed distinctive banded iron formations, BIFs. These formations, consisting of alternating layers of oxidized and unoxidized iron, are evidence of enormous changes in the chemical composition of oceanic water. The banded iron formations we can observe today in geological deposits were formed over a long period as millions of tons of iron oxides accumulated in the oceans. These layers changed the color of the oceans, which were originally greenish or gray, turning them blue. Approximately 100 million years after the start of the oxygen catastrophe, the oceans became more transparent, and their color resembled what we know today. This change in color is linked to a decrease in the concentration of dissolved iron, and an increase in the concentration of oxygen, which in turn facilitated the development of new forms of life. As a result of oxidation processes on the ocean floor, large iron ore deposits were formed, which became the basis for future industry. Around 2 billion years ago, when the level of oxygen reached significant values, BIFs began to disappear because the conditions for their formation no longer existed. Studies show that these iron formations cover a vast area on the planet, with a total area of more than 1 million square kilometers. These geological formations are not only a testament to the oxidative epoch, but also an important indicator of changes in Earth's ecosystems. Some organisms have adapted to new conditions, resulting from an increase in oxygen levels, and have developed unique protective mechanisms. For example, anaerobic bacteria, which initially thrived in low oxygen environments, began to evolve when they encountered an excess of oxygen. They learned to produce enzymes such as superoxide dismutase, which neutralize free radicals generated by oxidative stress. These enzymes help protect cells from oxygen-induced damage and enable survival in harsh environments. Meanwhile, other organisms like cyanobacteria found a way to use oxygen in their metabolic processes for photosynthesis. These single-celled organisms, which appeared around 3 billion years ago, began to release oxygen as a result of converting sunlight, carbon dioxide, and water into organic compounds. This process not only increased the oxygen content in the atmosphere, but also laid the foundation for the emergence of new forms of life. Gradually, oxygen became a necessary element for more complex organisms. Adaptation to an oxygen-rich environment led to what is known as adaptive radiation, where new and diverse forms of life began to appear. Around 1 billion years ago, protists emerged, which used oxygen to more efficiently obtain energy. These simple organisms became the ancestors of all multicellular beings. As a result of this adaptation and evolution, the first multicellular organisms, such as algae and sponges, developed structures and functions thanks to their highly efficient metabolism. For instance, chlamydomonas algae, which live in fresh water, have chloroplasts that allow them to use sunlight for photosynthesis and produce oxygen. These organisms became the basis for the formation of more complex ecosystems. A notable example is coral reefs, which developed in oxygen-rich water, providing shelter and food for numerous marine creatures. Adaptation to an oxygen-rich atmosphere also contributed to the emergence of complex multicellular organisms, such as the ancient ancestors of fish, which began to develop gills for breathing oxygen dissolved in water. Around 500 million years ago, during the Cambrian period, there was an explosion of biodiversity, with the appearance of groups like trilobites and brachiopods. These organisms demonstrated how oxygen became a driving force for evolution and the diversification of life forms on Earth. In this context, studying these processes helps us understand how oxygen paved the way for the development of more complex and energy-efficient organisms capable of occupying various ecological niches. An important fact is that it was the oxygen-rich atmosphere that led to the emergence of more complex forms of life, ultimately resulting in the appearance of vertebrates and other complex organisms. An eukaryotic cell is a more complex structure compared to prokaryotes, and this new type of cell can be visualized as a miniature city, where each part performs a specialized function. Inside these cells, there are various structures that can be compared to factories and control centers. These structures regulate metabolism, protein synthesis, and also provide protection and transport of substances. Eukaryotic cells contain a nucleus, where genetic material is stored in chromosomes, allowing for effective management of hereditary information. The appearance of eukaryotes was a revolutionary leap in the complexity of living systems, as they laid the foundation for the development of all higher forms of life on Earth. Eukaryotes first appeared around 1.8 billion years ago and became the ancestors of all multicellular organisms, including plants, fungi, and animals. This evolutionary revolution was made possible by the complex organization of cells, allowing them to perform multiple functions simultaneously. For example, due to internal membranes that create various compartments, eukaryotes can separate chemical reactions, increasing their efficiency. This ability to specialize is a key factor that allowed eukaryotes to adapt to various environmental conditions and develop more complex forms of life. Some researchers, such as Carl Woese, emphasize that the creation of the eukaryotic cell paved the way for the emergence of multicellular organisms, which in turn became the basis for the formation of ecosystems that we observe today. In an evolutionary context, eukaryotes are not just individual cells, but entire systems capable of interaction and self-regulation. Their ability to divide and differentiate cells led to the formation of tissues and organs, which became the basis for the formation of complex organisms. The existence of such cells made it possible to significantly increase the size of organisms and the complexity of their structures. This is evident in the fact that some eukaryotes, such as trees or whales, can reach gigantic sizes, while others, like amoebas, remain single-celled but are still eukaryotes. Eukaryotic cells became the basis for all forms of life that inhabit our planet, and their complex organization allows them to maintain life in the most diverse conditions. The number of eukaryotic organisms on Earth is counted in billions, and they are an integral part of the ecosystem, ensuring the exchange of matter and energy. The theory of endosymbiosis, proposed by Lynn Margulis in the mid-20th century, explains the origin of mitochondria as a result of symbiotic interaction between different cells. Approximately 2 billion years ago, ancient bacteria capable of aerobic respiration and effectively using oxygen for energy were engulfed by larger anaerobic cells. This process was akin to one organism becoming a home for another. But instead of being digested, these bacteria began to develop inside their hosts. The result of this symbiotic interaction was the emergence of mitochondria, which became the energy stations of cells. They provided the organism with additional energy in the form of adenosine triphosphate, ATP, enabling larger cells to develop and evolve into multicellular organisms. This remarkable cooperation became the driving force of evolution. Mitochondria retain their own circular DNA, which is structurally very similar to prokaryotic DNA, serving as a compelling evidence of their bacterial origin. Their genetic code includes around 37 genes that encode proteins necessary for mitochondrial function, making them unique compared to other cellular organelles. This genetic material is transmitted only through the maternal line, further confirming their independent origin. Mitochondria not only participate in energy production, but also play a key role in regulating metabolism, apoptosis, and maintaining cellular homeostasis. This cooperation between bacteria and cells became the foundation for complex life on Earth, paving the way for the emergence of plants, animals, and ultimately humans. Mitochondria, maintaining their autonomy, continue to perform their functions in the modern organism. For example, human mitochondria can produce up to 90% of the energy needed for cellular processes. The complexity and beauty of this symbiosis are astonishing. Two different organisms united, creating something greater than the sum of their parts, which became the basis for multicellular life. The origin of chloroplasts is an intriguing example of endosymbiosis that occurred more than 1 billion years ago. Ancient photosynthetic cyanobacteria, with their unique ability to convert sunlight into chemical energy, were engulfed by eukaryotic cells that could not produce their own energy. This process essentially laid the foundation for the formation of chloroplasts, cellular organelles that function as solar batteries. As a result of the symbiosis, cyanobacteria lost their independence and became an integrated part of eukaryotic cells. This partnership allowed cells to directly use solar energy, marking a revolutionary moment in the evolution of life on Earth. Around 800 million years ago, this event led to the emergence of the first algae, simple plants that began actively colonizing aquatic ecosystems. Algae, in turn, became the basis for more complex forms of life, such as mosses and ferns, and eventually all terrestrial plants. It is important to note that it was chloroplasts that allowed plants to produce oxygen during photosynthesis, radically altering the composition of Earth's atmosphere. The oxygen released by plants became essential for the life of aerobic organisms. Currently, it is believed that approximately 30% of the oxygen we breathe is produced by oceanic algae. This underscores the significance of chloroplasts, as they not only provide energy to plants, but also support life on the planet as a whole. The evolution of chloroplasts became a key moment in the formation of ecosystems where plants play a central role in food chains and are the primary producers. Multicellularity is one of the most significant evolutionary transformations in the history of life on Earth. This transition from single cells to multicellular organisms occurred approximately 1 billion years ago, and led to the emergence of complex life forms that we observe today. Initially, cells began to form colonies, which can be compared to primitive human communities where individuals united to achieve common goals. These colonies allowed cells to interact with each other, share resources, and protect themselves from external threats. However, true multicellularity requires more complex organizational levels, where cells sacrifice their individuality to create something greater. This process can be likened to a society where each member performs a unique role, leading to higher levels of efficiency. Specialization of cells allowed them to perform various functions. Some cells became responsible for nutrient absorption, others for protecting the organism, and still others for signal transmission. This approach significantly increased the chances of survival in complex environmental conditions where resources may be limited and the threat from predators increases. Effective use of resources became possible because cells, united together, could work in synergy, leading to more efficient metabolic exchange and increased resistance to stressful conditions. Multicellular organisms can adapt to changes in their environment, making them more resilient compared to single cells. For example, in conditions of oxygen deficiency, multicellular organisms can alter their metabolic activity, reducing resource consumption. This became possible because cells began to interact with each other through specialized signals, creating complex communication systems. Such organisms typically have a higher level of organization, with differentiated tissues and organs, enabling them to perform complex biological functions. As a result, multicellular organisms, with their diversity of specialized cells, can better respond to changes in their environment, promoting their survival and prosperity. For example, in multicellular organisms, tissues such as nervous, muscular, and epithelial tissues form, each performing specific functions, which is not possible for single cells. This level of organization opens new horizons for growth and development, ultimately leading to the emergence of complex ecosystems where multicellular organisms became dominant. Specialization of cells, in turn, allows the organism to be more efficient in resource use, which is critically important in conditions of competition for survival. Thus, multicellularity not only increases the chances of survival, but also opens the way for the formation of complex structures such as organs and organ systems, which to a large extent determine the viability and adaptability of organisms. Scientific research shows that it was precisely due to multicellularity that various ecosystems and biodiversity on the planet developed. The Ediacaran biota appeared on Earth approximately 600 million years ago and represents some of the earliest known complex multicellular organisms. These creatures inhabited ancient oceans and had unusual soft bodies lacking hard skeletons, making them quite unlike modern animals. Most of them had disc, feather, or mattress-like shapes with characteristic patterns reminiscent of quilted blankets. For instance, one of the most well-known representatives, Dickinsonia, could reach a length of up to 1 meter and had a flat, oval body covered in segmented patterns, giving it the appearance of a giant sea mushroom. The Ediacaran biota led a slow-paced life, crawling along the seafloor and ingesting nutrients from water or sediment, which allowed them to survive in conditions of low oxygen availability. Some of these creatures, such as Charnia, were attached to substrates and resembled plants, although they were actually animals. Their enigmatic nature has led to numerous debates about which groups of organisms they belong to, as many of them do not fit into familiar categories like vertebrates or invertebrates. Research conducted in 2006 showed that some of these organisms could be predecessors of modern jellyfish and sea anemones, while others, such as Sprigina, resemble early chordates. These creatures lived in conditions where oxygen levels were significantly lower than today, and it is possible that this adaptation to extreme conditions contributed to their diversity and evolutionary success. Scientists studying the Ediacaran biota note that many of these organisms had unique feeding methods, including filtering nutrients from water, suggesting that they had entirely different mechanisms of interaction with their environment. The enigma of the Ediacaran organisms is not limited to their appearance. Some of them, such as Rugosa, have strange spiral-like forms that challenge traditional notions of what multicellular organisms should look like. Research conducted in 2015 showed that the Ediacaran biota could have existed in conditions with significantly higher levels of ultraviolet radiation, which may have contributed to their unusual structure. The existence of these organisms ended approximately 500 million years ago, when the Cambrian period began, marked by a rapid explosion of new life forms. However, their legacy continues to raise many questions in the scientific community. The Ediacaran biota remains an active area of research, and scientists continue to discover new fossil remains that may shed light on their biology and their place in the evolutionary history of our planet. The Cambrian explosion is a period that began around 530 million years ago and lasted for about 20 million years. During this time, a true revolution occurred in the world of living organisms. Nearly all the main groups of animals that exist today appeared on Earth. Oceans, once inhabited by simple organisms, suddenly teemed with a diversity of life forms, including creatures with shells, claws, and even jaws. During this time, evolution, like an experimenter, tested various survival and adaptation strategies to the surrounding environment. Scientists note that it was during the Cambrian period that animals were differentiated into such groups as arthropods, mollusks, and chordates. For example, fossilized remains of ancient trilobites, which became one of the symbols of this period, demonstrate how rapidly marine life developed. These creatures possessed complex anatomy, including a hard exoskeleton that protected them from predators and helped them survive in various conditions. At this time, the first predators, such as annelids and primitive vertebrates, began actively hunting less protected ocean inhabitants. This process became an important factor in natural selection, contributing to further evolutionary development. The Cambrian explosion gave rise to numerous new adaptations, including the development of eyes, which allowed animals to better navigate the aquatic environment. Researchers like David Brown and his team show that the increase in oxygen in the oceans led to a rapid increase in metabolism in many marine organisms, which in turn facilitated the appearance of more complex forms of life. Data from fossils indicate that during this time, the diversity of ecosystems reached its peak, with numerous niches for habitation, opening new horizons for adaptation and survival. It is interesting that during this time, organisms such as conchilians, ancestors of modern mollusks, began to occupy new ecological niches. The existence of such forms of life contributed to the formation of complex ecosystems, which in turn led to the development of new species capable of competing for resources. During this time, the waters were inhabited by true predators, such as the ancestors of modern octopuses, which used their cunning tactics for hunting. All these changes occurred in a relatively short period, which causes amazement and admiration in scientists trying to understand how and why this explosion of diversity occurred. There are hypotheses that climatic changes associated with tectonic activity and changes in sea level created new conditions for the life of marine organisms, contributing to their rapid development and adaptation. Around 200 species of animals, known from fossil remains, appeared during this period, including such ancestors as Pentamerus and Opabinia, which demonstrate an incredible diversity of forms and functions. The Cambrian explosion is not just an era, it is a moment in the history of life on Earth when evolution, as if, opened Pandora's box and allowed creatures to reveal all their potential. Burgess Shale is a unique fossil deposit located in the Canadian Rockies, offering a window into Cambrian life. These shales, which are over 500 million years old, were discovered in the early 20th century and have since become a sensation for paleontologists. The exceptional conditions in which these shales formed have allowed for the preservation not only of hard parts of organisms, such as shells and exoskeletons, but also of soft tissues, which is extremely rare in the fossil record. Over 600 species of organisms have been found in the Burgess Shale, including many with bizarre body forms that have no modern counterparts. For instance, creatures like the morella with its long body and numerous appendages, and the Opabinia, which had a unique set of 5 eyes and a long body with a tail resembling an antenna. This diversity of forms and functions has led scientists to re-evaluate traditional views on early animal evolution. One of the most significant discoveries is the so-called primitive jellyfish, which demonstrated that soft-bodied organisms were widespread long before the appearance of the first vertebrates. The Burgess Shale also contains fossils of creatures like the helminthoid, which looked like a giant worm, and the picaia, resembling a modern marine worm, but with unique features such as a segmented body and complex appendages. These finds have provided scientists with an incredible amount of information about Cambrian marine ecosystems, allowing us to see how complex organisms evolved. Studies of the Burgess Shale were initiated by paleontologists like David E.G. Scott and others, who emphasized that these fossils are key to understanding the origins of many modern animal groups. Thanks to the exceptional preservation of the fossils, researchers have been able to study the morphology and anatomy of these ancient organisms, not only at the level of their external appearance, but also at the cellular level. For example, microscopic studies have revealed the structure of soft tissues such as muscles and nervous systems, giving insight into how these organisms could move and react to their environment. The Burgess Shale is not just a treasure trove of fossils, but a living laboratory for studying early life on Earth, where each rock holds secrets of the ancient world. These discoveries are changing our understanding of how life developed in those distant times when large terrestrial animals did not yet exist, and marine creatures reigned, whose forms and functions become increasingly mysterious with each new discovery. As a result of studying the Burgess Shale, we now know that many ancient organisms had complex structures that preceded many modern animal groups, including chordates. The Burgess Shale is not just a historical fossil deposit. It is a living testament to how life on our planet evolved and adapted in the conditions of ancient oceans. The Paleozoic era, spanning from 600 million to 250 million years ago, was a pivotal phase in Earth's history, laying the foundation for contemporary biodiversity. During this time, life on the planet underwent significant transformations, evolving from simple single-celled organisms into complex multicellular forms. The Paleozoic era was the stage for the formation of the first ecosystems, where new ecological niches were created, opening avenues for further evolution. Initially, marine ecosystems dominated, with diverse invertebrates like trilobites and brachiopods thriving, employing various feeding and reproductive strategies. As evolutionary progress unfolded, new groups of organisms began to colonize new habitats. Key evolutionary innovations, such as rigid exoskeletons and respiratory systems adapted for terrestrial life, played crucial roles in this process. One of the significant achievements of the Paleozoic era was the emergence of the first land plants, which in turn facilitated the colonization of land by animals. It is noteworthy that the first forests, composed of mosses and ferns, not only served as a source of oxygen, but also provided new ecosystem services like water retention and soil formation. The appearance of insects in these forests played a pivotal role in establishing complex food chains and interactions among species. Concurrently, in marine environments, competition and adaptation led to the emergence of the ancestors of modern fish, which significantly increased their diversity through the evolution of various forms and strategies. The Paleozoic era was a time when life began to actively experiment with forms and functions, ultimately resulting in the formation of new taxa and ecosystems. By the end of this era, life on Earth had significantly diverged from its initial state. A critical aspect was that the Paleozoic era concluded with a mass extinction, causing the disappearance of over 90% of marine species, which opened new horizons for further evolutionary development. Such events, like this extinction, underscore the fragility and dynamism of ecosystems, which were not only formed but also destroyed, creating new opportunities for life. Evolution in the Paleozoic era laid the groundwork for contemporary ecosystems, establishing a foundation for subsequent stages in the history of living organisms. The Paleozoic era, without a doubt, was a crucial period when life on Earth began to explore new frontiers, expanding its boundaries and creating the diversity of forms we observe today. During the Silurian period, which lasted approximately from 430 to 440 million years ago, significant changes occurred on Earth, affecting not only the animal world but also the vegetation. On land, the first terrestrial plants began to appear, which were still very primitive and differed from modern forms. These plants, such as xylophytes, lacked roots, leaves, and flowers. Their stems resembled low green tubes rising above the wet soil of coastal zones. They seemed like the vanguard of a great conquest of land, ready to colonize new territories. These pioneers of life on land had to adapt to completely new conditions. For example, the absence of roots meant they could not extract water from the soil, which posed enormous challenges in the struggle against desiccation. To survive, plants developed mechanisms to retain moisture, such as a waxy layer on their stems that protected them from evaporation. Additionally, to support their bodies against the force of gravity, they had to develop rigid cells that provided the necessary support without hindering their growth. The dispersal of spores became another crucial task for these primitive plants. They needed to find ways to spread their spores over long distances without the help of water, which required not only adaptation but also ingenuity. These plants used wind to disperse their spores, allowing them to enter new ecosystems and colonize new areas of land. Thus, the Silurian period became a significant stage in the evolution of Earth's flora, when life began to actively explore new frontiers, and the first terrestrial plants laid the foundation for future forests and diverse ecosystems. At this time, the first reefs and marine ecosystems also appeared, creating conditions for further development of life on the planet. The Silurian period marked the beginning of a new era in which life on land and in water developed in parallel, creating an astonishing diversity of forms and adaptations. The Devonian period, which lasted from approximately 440 to 368 million years ago, is known as the Age of Fish. The oceans of that time became arenas for countless fish species that began to actively evolve. During this period, jawless fish like the lamprey appeared, which fed by sucking blood from other marine creatures. Their worm-like bodies were perfectly adapted to life in the dark depths of the oceans. Armored fish, such as osteichthyons, covered in bony plates, provided reliable protection from predators, with their unique shapes and sizes ranging from a few centimeters to several meters in length. Cartilaginous fish like sharks began to develop with powerful jaws capable of tearing flesh. Their early ancestors, such as sharks from the genus Cladocelac, existed around 360 million years ago and possessed unique features like long and sharp teeth, making them excellent predators. Bonefish, which appeared later, had swim bladders that allowed them to control their buoyancy and inhabit various water levels. These fish, particularly those in the order Actinopterygii, became the dominant inhabitants of the seas due to their ability to rapidly adapt and diverse hunting strategies. In the Devonian oceans, coral reefs also thrived, serving as homes for numerous marine creatures. Devonian coral reefs consisted of various species like rugosa and tabulata, which formed complex ecosystems attracting many fish and other marine creatures. These reefs not only provided shelter and hunting grounds, but also served as breeding sites. Deep sea zones were inhabited by strange bioluminescent predators that used bioluminescence to attract prey in the dark waters. Among them were creatures like the lancelet and early forms of eels that hunted in absolute darkness, relying on their unique sensory abilities. The combination of these factors made the Devonian period one of the most significant stages in the evolution of marine life, when the diversity of fish reached unprecedented levels. Towards the end of the Devonian period, around 360 million years ago, giant sharks like Dunkleosteus could reach lengths of over 8 meters and were among the largest predators of their time. At the end of the Devonian period, approximately 360 million years ago, the first tetrapods appeared on the evolutionary stage, becoming a crucial link between aquatic and terrestrial life. One of the most well-known representatives of this transitional group is Tiktaalik, which combined features of fish and early terrestrial vertebrates. This predator, measuring about 2.5 meters, had both gills and lungs, allowing it to adapt to various habitats. Its fin-like limbs were partially transformed, enabling it to move in shallow water and even on land. Tiktaalik lived in marshy coastal zones where shallow rivers and freshwater bodies would dry up, creating unique ecological niches. These places teemed with diverse life, and Tiktaalik's ability to move on land allowed it to avoid predators and find new food sources. Acanthostega, another member of this group, also exhibited similar transitional features. It had 4 limbs that were more developed than those of Tiktaalik and could use them to crawl on the soft bottom of water bodies or on land. These animals were adapted to environments where water levels could change rapidly, giving them an evolutionary advantage. Along with the development of limbs, changes occurred in the structure of the pelvis and spine to support weight on land. They could breathe both underwater and on land, allowing them to effectively utilize both types of habitat, which was crucial in the variable climate of the Devonian period. Direct ancestors of modern amphibians, such as Tiktaalik and Acanthostega, laid the foundation for further evolution of tetrapods. ultimately leading to the emergence of the first reptiles and mammals. These animals not only transformed the ecosystems of their time, but also laid the groundwork for future evolutionary changes, enabling vertebrates to occupy new ecological niches on land. Tiktaalik, in particular, is one of the most studied fossils, dating back approximately 350 million years, and its discovery in 2006 in Canada caused a sensation in the scientific community, confirming the theory of the transition from aquatic life to terrestrial life. Coal forests were an extraordinary phenomenon that existed on Earth approximately 300 million years ago. These ancient ecosystems covered vast territories, transforming the planet into a green kingdom teeming with life, yet completely different from modern forests. Wet, marshy conditions fostered the growth of giant ferns, horsetails, and club mosses, creating a unique forest structure. The height of these plants could reach 20 meters, forming a dense canopy of leaves that shaded the ground and created special microclimates. Unlike today's forests, where flowering plants and grasses dominate, coal forests were global centers of spore-bearing plants. They lacked flowers, and their reproduction depended on the dispersal of spores, resulting in a completely different landscape. The soft, damp air, rich in moisture, was filled with the aromas of decaying plant remains, which created a thick layer of organic matter on the surface of the Earth. These forests were the primary source of carbon, which later became trapped in sedimentary rocks and formed the basis for the coal that we use today. Primitive animals, such as early amphibians and insects, also inhabited these forests, adapting to life in this ecosystem. Many of them could be seen crawling among the roots and stems of the giant plants. The conditions in these forests were alien to modern understanding of flora and fauna. The absence of flowering plants created not only a unique visual appearance, but also a completely different biochemical composition of the atmosphere. The oxygen content during that period was significantly higher than it is now, which facilitated the growth of large insects such as the meganeura, with a wingspan of up to 60 centimeters. These forests not only shaped the climate, but also served as the source for future coal deposits, which became the foundation for the Industrial Revolution. Coal forests gradually disappeared with the advent of drier climatic conditions and competition from flowering plants, leaving behind only geological traces in the form of coal seams. The coal formed from the remains of these forests still plays a crucial role in the modern world, meeting the energy needs of many countries. Giant insects of the Carboniferous period were not just mythical creatures, but a reality that existed on Earth more than 300 million years ago. During this time, dragonflies could have wingspans of up to 70 centimeters. These magnificent creatures, with their extraordinary agility, soared over ancient swamps, hunting small vertebrates and other insects. Essentially, they were the predators of their time. For instance, a species of dragonfly known as Meganeura, which inhabited swamps in present-day France and Belgium, was one of the largest flying insects that ever lived. Millipedes of the Carboniferous period, such as Arthropleura, could reach lengths of more than 2 meters. Their massive bodies allowed them to efficiently move through the wet tropical forests where they preferred to hide, hunting small animals. The exceptional sizes of these arthropods were due to the high oxygen content in the atmosphere, which reached up to 30%, facilitating effective gas exchange and organism growth. Giant scorpions like Pulmonoscorpius also inhabited these ecosystems. They could grow up to 40 centimeters long and hunted smaller invertebrates and even small vertebrates. These predators used their powerful pincers to capture prey and their venomous stings for defense against larger predators. Spiders like Megarachne could reach sizes comparable to modern lizards and used their webs to trap prey, creating traps in dense undergrowth. These giant arthropods dug burrows in soft soil, creating complex underground tunnel systems that allowed them to hide from predators and protect themselves from adverse weather conditions. Their biology and ecology were unique, as they adapted to environments where resource competition was less intense and the ecosystem was rich in diverse forms of life. High oxygen levels and abundant vegetation, including giant ferns and mosses, created ideal conditions for their existence and growth. These factors contributed to the flourishing of giant insects, which became dominant predators in their ecosystems. Evidence of their existence is found in the form of fossils that confirm their sizes and diversity. Fossils of Arthropleura have been found in layers dating back to the late Carboniferous period, on the territories of present-day United States and Europe. These discoveries indicate that giant insects not only existed, but also played a significant role in the ecosystems of their time, forming food chains and influencing the development of the surrounding environment. Coal is formed from the remains of ancient plants that accumulated on the bottom of boggy water bodies over millions of years. This process began in the Devonian period, approximately 360 million years ago, when Earth was covered with vast forests composed mainly of ferns and coniferous plants. As these plants died, their remains sank into acidic, oxygen-poor soil in the bogs. Under these conditions, decomposition occurred slowly. Water and soil hindered the breakdown, preserving the plant material in its original form. The accumulation of plant remains continued for millions of years, forming multi-layered deposits that were eventually covered by new layers of vegetation and sediments. Over time, under the pressure of overlying strata, these layers transformed into peat and then into coal. Each layer represents a snapshot of the ecosystem of its time, preserving the history of flora and fauna of that period. The carbon contained in coal is the result of the photosynthetic activity of these ancient plants, which used solar energy for their growth. These coal deposits, located at depths ranging from several tens to several hundred meters, serve as a kind of time machine, allowing us to extract and utilize solar energy accumulated by plants hundreds of millions of years ago. Coal mines around the world, such as those in Pennsylvania and West Virginia, enable the extraction of this fossil fuel, which in turn became the foundation for the development of energy and industry in the 20th century. Each time we burn coal to generate electricity, we are essentially initiating a process that began in prehistoric times, when Earth was covered with forests of giant ferns and coniferous trees. The layers of coal can reach thicknesses of over 100 meters, and its reserves in some regions can amount to billions of tons. As a result of intensive coal mining, it is evident that this fossil energy continues to have a significant impact on the modern economy and climate, posing serious environmental challenges. Coals formed in different geological epochs vary in their composition and quality, making coal one of the most diverse fossil energy resources on the planet. The Permian extinction, which occurred around 250 million years ago, was the greatest mass extinction in the history of our planet, wiping out approximately 90% of all species that existed at the time. This catastrophic event led to the near-total destruction of existing ecosystems, making Earth a place where life teetered on the brink of collapse. For a long time, the biosphere was closest to its complete annihilation, and the consequences of this extinction were felt for millions of years. Many ecosystems that served as the foundation for life were wiped off the face of the Earth, leaving behind only dead lands covered in ash and barren landscapes. As a result of this event, not only marine creatures like trilobites and certain groups of corals, but also terrestrial animals, including the ancestors of modern mammals and reptiles, went extinct. The recovery of ecosystems after the Permian extinction was a true test for life on Earth. Ecosystems began to recover slowly, a process that took around 30 million years before the planet once again became home to diverse forms of life. During this time, significant changes occurred on the planet. New ecosystems formed, which later became the basis for life in the Mesozoic era. The recovery of the biosphere was characterized by the appearance of new species and groups of organisms that adapted to the changed conditions of life and filled the ecological niches left by the extinction. Throughout this long and complex period, life on Earth not only recovered but also developed, ultimately leading to the appearance of dinosaurs. The Permian extinction served as a reminder of the fragility of life and how quickly the world can change under the influence of catastrophic natural forces. It is important to note that to this day, not all aspects of this event are fully understood by scientists, and many hypotheses about its causes and consequences continue to be discussed and researched. To date, this extinction has become an important object of study for paleontologists and geologists who are striving to understand the mechanisms behind such global ecological crises in order to better cope with possible similar situations in the future. The Permian extinction remains one of the most dramatic and mysterious pages in the history of Earth, embodying the power of nature and its ability to destroy. Siberian traps. This is a colossal volcanic event that occurred approximately 240 million years ago and could have been one of the key causes of the Permian extinction. These massive eruptions covered areas comparable in size to modern Europe and lasted for hundreds of thousands of years. The volcanic layers formed as a result of these eruptions can reach a thickness of up to 1 kilometer and extend over an area of more than 1 million square kilometers. As soon as the volcanoes began to erupt, lava flows of molten rock filled vast spaces, creating unique landscapes that we see today. Giant volumes of carbon dioxide and sulfur compounds were released into the atmosphere, leading to rapid climate changes. Scientists have calculated that the release of carbon dioxide could have increased its concentration in the atmosphere to 30%, which in turn caused a greenhouse effect. Together with sulfur compounds, this created conditions for acid rain, which destroyed ecosystems and caused mass extinction of species. These volcanic activities, in addition to their destructive effects on land, also affected the oceans, where the acidity sharply increased, leading to the death of marine organisms. Research shows that as a result of these catastrophic changes, more than 90% of all species that inhabited the planet, including many marine organisms and terrestrial animals, became extinct. Siberian traps embody the catastrophic forces of nature that can fundamentally change the Earth's climate system and cause global ecological crises. Near modern cities such as Krasnoyarsk and Irkutsk, traces of these ancient eruptions can be found, testifying to the fact that the power of the volcanoes was so great that it could change the course of life on Earth. Volcanic activity in Siberia, it is likely, served as a catalyst for other ecological changes that accumulated like a snowball, leading to one of the most severe mass extinctions in the history of our planet. Siberian traps, with their volcanic formations and enormous lava flows, serve as a reminder of the powerful processes that occurred on Earth and how they could influence life on a global scale. This is evidenced by the results of research conducted by geologists such as Professor Mikhail Kokorin, who noted that the scale of the eruptions and their consequences remain a subject of active study and discussion in the scientific community. The Mesozoic era, spanning from 253 to 66 million years ago, is often referred to as the Middle Age of Earth's history, situated between the Permian and Cretaceous Paleogene mass extinctions. This period was not just the time of reptiles, as commonly believed, but also saw the emergence of numerous other groups of organisms that filled the ecological niches left vacant by the catastrophe that wiped out nearly 90% of all species. Following the Permian extinction, Earth was characterized by vast deserts and rocky landscapes where life was just beginning to recover. Around 2 million years later, during the Triassic period, the first dinosaurs, such as Eoraptor, which lived around 230 million years ago, began to appear on the planet. At the same time, mammals were actively developing, although they remained small and inconspicuous compared to the dominant reptiles. The Triassic period also saw the emergence of the first lizards, leading to significant changes in ecosystems. In the Jurassic period that followed the Triassic, giant dinosaurs like Brachiosaurus and Tyrannosaurus rex, reaching lengths of up to 30 meters, dominated the Earth. This period also witnessed the appearance of the first birds, such as Archaeopteryx, which began to explore the skies, becoming the first representatives of a class that would later evolve into modern birds. Meanwhile, marine life was represented by numerous forms, including giant mosasaurs and plesiosaurs that ruled the oceans. The Mesozoic era was marked by significant evolutionary innovations and adaptations. Flowering plants began to develop in the late Jurassic period, altering the landscape and ecological interactions on land. These organismal changes led to the creation of new ecosystems where dinosaurs, mammals, and vegetation coexisted, creating a rich diversity of life forms. Towards the end of the Mesozoic era, during the Cretaceous period, reptiles reached their peak, but also witnessed the emergence of new groups of organisms, such as modern insects and flowering plants, which began to dominate the ecosystems. The Cretaceous Paleogene extinction event, which occurred around 60 million years ago, marked the end of this era and the reign of dinosaurs. This period, filled with evolutionary innovations and ecological changes, laid the foundation for the future diversity of life on Earth. It is important to note that the Mesozoic era, often perceived as the era of reptiles, was not just the time of dinosaurs, but also saw the active evolution and adaptation of many other forms of life in response to changes in their environment. Besides reptiles, there were also mammals, birds, and a wide variety of marine organisms that filled all available ecological niches. The Triassic period, which began around 246 million years ago and lasted until 240 million years ago, marked a significant milestone in the history of Earth, signaling the recovery of life after the catastrophic Permian extinction, which wiped out approximately 90% of all species. This period was characterized by a slow but steady recovery of ecosystems, where a few surviving groups of organisms, such as certain amphibians and reptiles, began to fill the vacant ecological niches. During this time, on the vast supercontinent Pangaea, the climate became predominantly hot and arid, creating conditions for the formation of new ecosystems. Its territory included vast deserts, and coastal areas saw the emergence of shallow marine ecosystems. As a result of adaptation to these conditions, new groups of reptiles began to appear, among which the ancestors of dinosaurs, crocodiles, and turtles stand out. They began to diversify actively, occupying various ecological niches, from small forms like archosaurs to larger species capable of hunting other animals. For example, in the Triassic, the genus of dinosaurs known as Dilophosaurus appeared, becoming one of the first large predators of its time, reaching lengths of up to 6 meters. This period also witnessed the appearance of simple turtles that began to colonize aquatic and semi-aquatic habitats, further increasing the diversity of ecosystems. The diversity of flora also increased. During this time, conifers and horsetails began to dominate, creating dense forests and providing a new level of ecosystem interactions. An important element of the Triassic period was also the active volcanic activity, which contributed to climate change and the formation of new landscapes. For example, in central Portugal, traces of volcanic activity are preserved, which shaped the relief and ecosystems, allowing various groups of organisms to adapt to new conditions. Despite being a period of recovery, it also posed serious challenges for organisms, such as competition for resources, climate change, and the possibility of new extinctions. As a result of these processes, the world gradually filled with life, and ecosystems began to acquire complexity and diversity that would serve as the foundation for future epochs. During this time, significant evolution also occurred. Reptiles adapted to various habitats, leading to the appearance of the first ancestors of modern mammals. For example, small mammals like Triassic synapsids began to develop in competition with reptiles, which would later pave the way for evolutionary paths that would change the world. The Triassic period served as a starting point for the formation of ecosystems that would dominate the planet for millions of years, clearly demonstrating how life can recover and adapt even after the most catastrophic events. By the end of the Triassic period, around 240 million years ago, reptiles had already occupied significant niches in ecosystems, foreshadowing their dominance in the Mesozoic era. Pangaea was an ancient supercontinent that existed approximately 300 million years ago and united nearly all of Earth's landmass into a single massive entity. Imagine a colossal block of land surrounded by the majestic ocean of Panthalassa, which stretched from pole to pole and covered about 90% of Earth's oceanic area. This was not merely a geographical formation, but a whole ecosystem with climatic conditions vastly different from today's. Within Pangaea, continental climatic zones prevailed, ranging from tropics to temperate latitudes, creating diverse living conditions. Giant insects like the Meganeura, with wingspans of up to 60 centimeters, and primitive reptiles that were just beginning to evolve inhabited its territory. Pangaea's influence on climate was immense. A dry climate dominated the center of the continent, while coastal regions enjoyed more humid and temperate conditions. Due to its continental location, unique oceanic currents formed, distributing heat and moisture across the planet. These currents also influenced the migration of marine organisms, fostering their evolution. Pangaea existed during a time when Earth's crust was particularly active, and tectonic processes led to the formation of mountain ranges like the Appalachians and the Urals. These mountains, formed by the collision of tectonic plates, created barriers for animal and plant migration, contributing to their evolution into unique species. As Pangaea began to break apart around 180 million years ago, the animals and plants that had evolved in these isolated ecosystems started to adapt to new conditions. The breakup of Pangaea was a pivotal moment in Earth's history, opening new migration paths for life, while climate changes brought about by the formation of new oceans and continents acted as a catalyst for further evolution. Scientific research by geologists and paleontologists shows that this process led to the emergence of new species and their dispersal across various regions. For instance, dinosaur fossils found in different parts of the world indicate that despite the separation, some species continued to migrate and interact, ultimately resulting in the biodiversity we observe today. Pangaea, as a colossus of its time, set the tone for evolutionary processes on Earth, shaping a world where life could both adapt and develop in conditions we can barely imagine. The size and structure of this supercontinent created unique conditions for the formation of ecosystems that acted as incubators for new forms of life. In the interior regions of Pangaea, far from the oceans, unique climatic conditions were formed that defined the ecosystems of this supercontinent. These vast territories were subject to extreme continental climate, where summer temperatures could reach 45 degrees Celsius, while winter temperatures dropped to -30. Central areas of Pangaea, such as the present-day regions where the Namib and Kalahari deserts are located, were covered with giant sand dunes and rocky landscapes. Here, amidst the barren expanses, rare oases, surrounded by small lakes and rivers, served as the only habitats for plants and animals. In these isolated water bodies, such as small rivers winding through the desert, life found refuge despite the harsh conditions. For example, oases could support ecosystems where date palms and other drought-adapted plants, like acacia trees that could store water in their stems, grew. In such conditions, survival required unique adaptations from animals. Many species developed the ability to live for long periods without water, while some, like the ancient ancestors of modern lizards, could hide in burrows to avoid the heat. These desert regions were also home to species like dinosaurs of the theropod group, which adapted to the harsh conditions by developing lightweight bodies and effective hunting strategies. There were even entire ecosystems where animals and plants had mutually beneficial relationships, such as certain types of cacti that attracted pollinators like ancient insects to ensure their reproduction. Deep rivers, like those that flowed in the present-day central regions of Africa, could form temporary water bodies that served as important habitats for animal migration, seeking food and water. These conditions led to a rigorous selection process, resulting in the survival of only the most resilient and adapted species. A remarkable example is the ancient plants like ginkgo, which survived changing climates and maintained their form over millions of years. These climatic conditions also contributed to the formation of salt pans, which occupied large areas and created unique landscapes known for their white saline deposits resulting from water evaporation. Ultimately, these harsh living conditions became a catalyst for the evolutionary diversity that we observe in the fossil remains and petrifications found in today's deserts and semi-deserts. Each of these conditions, every adaptation, and every form of life remind us of how complex and diverse the internal world of Pangaea was. 200 million years ago, at the end of the Triassic period, the unified continent of Pangaea began to break apart under the influence of powerful tectonic forces. This process was caused by the movement of Earth's mantle, which pushed continental crust masses in different directions, creating cracks and rifts. Initially, the images of these rifts were insignificant, but they soon became wide gaps where narrow marine straits began to form. For instance, the rift that formed between present-day Africa and South America became the foundation for the Atlantic Ocean. This ocean gradually increased in size, leading to the formation of new ocean currents that began to influence global climate conditions. Scientific research shows that during the breakup of Pangaea, such oceans as the Indian Ocean, which arose between Africa and Australia, and the Pacific Ocean, which expanded with each millimeter of rift in the continental crust, were formed. The breakup of Pangaea was not only a geological event, but also a catalyst for the evolution of life. Isolated landmasses became homes for unique life forms that adapted to new conditions. For example, dinosaurs that existed in various parts of Pangaea began to evolve into different species as the continents began to separate from each other. Each new ocean created new ecosystems that in turn contributed to the diversification of flora and fauna. For example, the formation of the Atlantic Ocean changed the direction of marine currents, affecting the water temperature and consequently the climate in adjacent regions. These changes opened new niches for life, allowing marine organisms such as corals and mollusks to occupy new territories. As a result, as the continents continued to move, They not only changed the geography of the planet, but also influenced the evolutionary processes that took place in the oceans. As the breakup of Pangaea continued, the size of the new oceans became impressive. For instance, the width of the Atlantic Ocean today reaches more than 4,000 kilometers, and its maximum depth is around 8,000 meters. This process lasted for millions of years and only ended in the late Cretaceous period when the new continents took their modern positions. Thus, the breakup of Pangaea not only changed the world map, but also became a grand stage for the evolution of life, forming unique ecosystems that we observe and study today. The Jurassic period, which lasted from 146 to 149 million years ago, was a time when dinosaurs finally established their dominant position among terrestrial vertebrates. During this period, there was a significant diversity of life forms, and dinosaurs adapted to a wide range of ecological niches, from carnivorous to herbivorous, and from small to giant sizes. On the Jurassic continents, such as Laurasia and Gondwana, diverse and rich ecosystems emerged. Wet forests, teeming with giant horsetails and ferns, provided habitats for numerous creatures. Some horsetails grew to heights of over 20 meters, and their roots strengthened the soil, creating stable ecosystems. Open plains were covered with cycads and ginkgos, which served as food for various herbivorous dinosaurs. These trees could reach heights of up to 30 meters and formed dense undergrowth where small mammals, such as Triceratops, could hide from predators. Coastal marshes and lagoons of the Jurassic period were home to many species, including marine reptiles like plesiosaurs and ichthyosaurs, which hunted fish and mollusks. The fauna was incredibly diverse, ranging from tiny mammals hiding in the undergrowth to giant sauropods like Brachiosaurus, which roamed in herds across open spaces. Brachiosaurus could reach lengths of up to 25 meters and weigh up to 60 tons, their long necks allowing them to reach high trees. At this time, there were also predatory dinosaurs like Allosaurus, which could reach lengths of up to 12 meters and actively hunted smaller dinosaurs and other animals. They developed powerful jaws and sharp teeth, making them effective predators. In such conditions, dinosaurs adapted and evolved, forming numerous species, each occupying its ecological niche and filling all available spatial and food niches. The Jurassic period ended around 144 million years ago, but its impact on the evolution and development of life on Earth remains significant to this day. During this period, dinosaurs not only dominated, but also created unique ecosystems that became the foundation for future generations of animals. Archaeopteryx is an extraordinary creature that became a symbol of the transition between reptiles and birds. About the size of a sparrow, it possessed unique features that combined elements of two different groups, dinosaurs and modern birds. For example, Archaeopteryx had teeth, a long bony tail, and claws on its wings, characteristics typical of reptiles. At the same time, its body was covered in feathers, and the tips of its wings had primary feathers, indicating its ability to fly. These feathers were likely not only for flight, but also for thermoregulation, making Archaeopteryx even more intriguing for study. Its legs had a structure similar to modern birds, including a wishbone, indicating the presence of more developed musculature for flight. Archaeopteryx lived in the forests of the Jurassic period, approximately 150 million years ago, and likely used its gliding ability to move from tree to tree, making short flights to find food or shelter from predators. The fossils of Archaeopteryx, first discovered in Bavaria in 1859, became a crucial confirmation of the theory of evolution. These finds demonstrated how one group of animals gradually transformed into another, serving as the foundation for further research in paleontology and evolutionary biology. In essence, Archaeopteryx is not just an intermediate form, it is a key to understanding the complex process of evolution, which continues to fascinate scientists worldwide. In its fossils, specialists have discovered not only typical reptilian and avian features, but also an extraordinary feather structure reminiscent of modern feathers, indicating its ability to fly. Archaeopteryx could hover in the air, gliding over short distances, allowing it to evade predators and search for food such as insects or small lizards. Its lifestyle was adapted to the conditions in which it lived, making it not only an interesting object of study, but also a vital link in the chain of evolution. The fossils of Archaeopteryx, with their clearly visible features, confirm that evolution is not a sudden leap, but a slow and gradual process. Comparing it with other species, such as Velociraptor and modern birds, one can see how adaptations of animals to their environment have changed over millions of years. The 8 specimens of Archaeopteryx found to date demonstrate its diversity and complexity, making it one of the most important objects in paleontology. The Cretaceous period was the final stage of the Mesozoic era, characterized by substantial changes in the planet's geology and ecology. During this time, continents continued to break apart, increasing the distances between them and altering climatic conditions, which led to the formation of new seas. Sea levels reached unprecedented heights, creating vast coastal ecosystems teeming with diverse life forms. This period witnessed unique evolutionary changes, such as the emergence of modern flowering plants, which began to reshape the Earth. These plants provided new food sources for animals, contributing to further biodiversity. Vast forests with diverse flora and fauna covered the continents, while extensive shallow seas served as homes for many marine creatures. Concurrently, other changes occurred. Predators began to occupy new ecological niches, adapting to the new conditions. Towards the end of the Cretaceous period, approximately 65 million years ago, one of the most famous mass extinctions in Earth's history took place, when around 75% of all existing species disappeared. This event was likely caused by a combination of factors, including the impact of an asteroid and volcanic activity, which led to abrupt changes in climate and ecosystems. The extinction of numerous species opened up new ecological niches, acting as a catalyst for further evolution and the rise of mammals, which would later dominate the planet. The Cretaceous period marked the final act in the symphony of the Mesozoic era, leaving behind a rich legacy and raising numerous questions about how life on Earth has changed over millions of years. The Mesozoic Sea, a vast shallow basin that covered significant areas of modern continents, was one of the most striking chapters in Earth's history. During this period, which lasted from 130 to 66 million years ago, the level of the world ocean significantly rose, flooding low-lying lands and creating expansive marine spaces. These warm and life-rich waters were an ideal habitat for numerous organisms. Ammonites, marine mollusks with characteristic spiral shells, thrived in these seas. Their diversity was astonishing. By the end of the Mesozoic period, there were over 100 species, some of which reached diameters of more than 2 meters. Also, in the Mesozoic Sea lived belemnites, relatives of ammonites, with elongated shells and a significant role in the ecosystem. In this rich environment, marine reptiles such as plesiosaurs and ichthyosaurs hunted fish and other marine creatures. These reptiles, majestic and graceful in their movements, could reach lengths of up to 7 meters. Primitive bony fish, such as the pederaspids, actively filled the water niches, creating complex food chains. The seafloor of this sea was covered with white chalky silt, composed of the skeletons of microscopic organisms like Radiolaria and Foraminifera. It was this silt that became the basis for the future chalk, giving its name to the entire period. During the deposition of these organisms on the seafloor, thick layers of limestone were formed, which later became the foundation for many well-known geological formations, such as chalk cliffs that can be seen in modern countries like the United Kingdom and France. For example, in Caen, on the coast of Normandy, chalk cliffs made of chalk rise to heights of up to 100 meters and serve as a vivid testimony to this period. Throughout the Mesozoic period, numerous ecosystems developed and changed, and on the backdrop of this richness of life, ecological changes occurred that preceded the next geological stage. The Mesozoic Sea not only served as a cradle for numerous species, but also as a stage for complex interactions between them, ultimately shaping a multifaceted and diverse world. Flowering plants, or angiosperms, began their triumphant march across the Earth during the Cretaceous period, which spanned from 130 to 66 million years ago. This era marked a true botanical revolution. Flowers with vibrant and eye-catching forms and scents began to displace the dominant gymnosperm plants, such as conifers. By the end of the Cretaceous period, flowering plants occupied more than half of all terrestrial ecosystems. Their success was driven by several factors, one of which was efficient reproduction. Flowering plants developed complex mechanisms to attract pollinators like bees, butterflies, and flies, increasing the chances of successful pollination and consequently reproduction. According to paleobotanists like Jonathan Gardner, At this time, insects were already actively interacting with flowers, facilitating their spread across all continents. In Cretaceous forests, magnolias, planes, and figs appeared, adapting to various conditions and becoming key components of these ecosystems. For example, magnolias, with their large and fragrant flowers, attracted numerous pollinators, enhancing their spread. Planes, with their distinctive leaves and fruits, created new ecological niches, providing shelter and food for various animals. These changes in vegetation led to the transformation of ecosystems. Forests became more diverse and productive. The appearance of flowering plants created new conditions for animal life, which began to adapt to new food sources and habitats. For instance, many bird species became dependent on the fruits and seeds of these plants. By the end of the Cretaceous period, flowering plants accounted for more than 70% of all plant species, confirming their dominance in the ecosystems of that time. The shift from gymnosperms to flowering plants was not just an evolutionary step, but a true ecological revolution that altered the face of the planet and created new opportunities for life. On continents like North America and Europe, dense forests filled with flowering trees emerged, forming the basis for complex food chains and new forms of life. Approximately 65 million years ago, at the end of the Cretaceous period and the beginning of the Paleogene epoch, one of the most catastrophic events in Earth's history occurred: the impact of the Chicxulub asteroid. This celestial body, with a diameter of about 10 kilometers, struck Earth in the region of present-day Yucatan Peninsula in Mexico. The impact was so powerful that it caused a blinding flash visible from hundreds of kilometers away. At the moment of impact, energy equivalent to 1 billion atomic bombs dropped on Hiroshima was released. As a result of this collision, the surrounding rock melted and vaporized, forming a massive crater with a diameter of about 130 kilometers, which can still be seen today. The shockwave generated a gigantic tsunami that devastated coastal areas, destroying everything in its path. Enormous volumes of dust and ash were ejected into the atmosphere, blocking out sunlight and causing a sharp drop in global temperature, leading to what is known as a nuclear winter. Global fires swept across vast territories, destroying forests and ecosystems. This climate change had catastrophic consequences for flora and fauna. The asteroid impact caused acid rain, which eroded soil and water bodies, exacerbating the situation. The collapse of photosynthesis led to the death of vegetation, disrupting food chains. Around 75% of all plant and animal species, including non-avian dinosaurs that had ruled Earth for millions of years, went extinct. Research shows that these events occurred over less than 100,000 years, which is an instant in geological time. The Chicxulub crater has become one of the key sites for studying this mass extinction, and its discovery in 1980 provided evidence of the connection between asteroid impact and global changes on Earth. The Chicxulub asteroid has become a symbol of the cosmic threat that could recur in the future. The Cenozoic era began approximately 66 million years ago and continues to the present day, representing a period of significant changes in Earth's ecosystems. This new era of life was marked by recovery and transformation, as ecological niches freed by the mass extinction at the Cretaceous-Paleogene boundary began to fill with new groups of organisms. During the first few million years of the Cenozoic era, Earth witnessed a rapid increase in the diversity of life forms. Mammals, birds, insects, and flowering plants emerged to occupy the spaces left by the extinction of dinosaurs and other species. Initially small and secretive, mammals began to evolve into larger and more diverse forms, ultimately leading to the emergence of groups such as primates, cetaceans, and carnivores. This evolution occurred against a backdrop of climatic changes that ranged from tropical forests to cold steppes and deserts. For example, during the Eocene epoch, roughly 50 to 34 million years ago, the planet's temperature was significantly higher than it is today, and regions now considered polar were covered in dense forests. At this time, flowering plants flourished, becoming dominant in ecosystems and providing a diverse range of food for many animals. Birds, which had begun to evolve from their ancestors during the Mesozoic era, became more adaptable and diverse, allowing them to occupy various ecological niches, from predators to pollinators. Throughout the Cenozoic era, insects also underwent significant changes, including the emergence of complex forms such as bees and butterflies, which played a crucial role in pollinating flowering plants. The Cenozoic era was not only marked by the rise of mammals, but also by the emergence of new ecosystems, such as savannas and forests, which provided unique conditions for the survival and adaptation of various life forms. There is evidence that during this period, important geological events occurred, such as the uplift of the Himalayas, which altered climatic conditions and contributed to the formation of new ecosystems. Over the last few million years, the Cenozoic era has also witnessed the appearance of humans, who, starting with their earliest ancestors, have had a significant impact on the environment. Human activities, such as agriculture and urbanization, have begun to alter ecosystems, creating new challenges for the survival of other species. The Cenozoic era, as an era of mammals, is also characterized by the remarkable development of life on Earth, making it unique in the planet's history. The size of some mammals, such as mammoths, reached more than 4 meters in height, demonstrating the extraordinary diversity and adaptability of life forms. As a result of all these changes, the Cenozoic era became not only the era of mammals, but also a time when life on Earth took on many forms, each with its own unique history and evolutionary path. The Paleocene is a period that began approximately 66 million years ago and lasted until 61 million years ago, immediately following the mass extinction of dinosaurs. At this time, Earth's conditions fostered adaptive radiation among mammals, which began to fill the ecological niches left vacant. These small, primitive mammals evolved into diverse forms, many of which had no modern counterparts. For instance, the pantodonts, which lived during this period, were large herbivorous mammals with massive jaws and teeth designed for chewing tough vegetation. They could reach sizes of up to 2 meters in length and possessed characteristics that made them resemble modern rhinos, although their lineage was entirely different. Mesonychids, another group of mammals from this time, were also distinguished by their unique appearance and lifestyle. These predators were similar to large dogs and adapted to hunting other animals using their sharp teeth and swift legs. They inhabited territories that are now part of North America and Europe and could reach the size of modern wolves. Multituberculates, or multituberculates, represented another unique example of early diversity. They had distinctive bumpy teeth that allowed them to consume various types of food, including insects and soft fruits. These animals also did not survive to our time, giving way to more specialized forms. Many of these groups of mammals can be seen as evolutionary experiments, as they demonstrated diverse adaptations to their environment, but most of them proved unsuccessful and soon disappeared, leaving only traces in fossil records. Scientific research conducted in the 12th century showed that many of these mammals shared common ancestral lines with modern forms, but their evolutionary paths diverged when more successful species began to occupy the vacant niches. As a result, the Paleocene became an era when mammals began to actively colonize diverse ecosystems, creating conditions for the future dominance of this class of animals on the planet. Throughout the entire Paleocene, mammals continued to evolve, and by the end of this period, they had already begun to form their own ecosystems, which ultimately led to the emergence of more complex forms of life in subsequent epochs. Among them were early primates, which began to develop in tropical forests and laid the foundation for the further evolution of mammals, including humans. The formation of the Himalayas is one of the most remarkable examples of mountain building in the Cenozoic era, resulting from the collision of the Indian and Eurasian tectonic plates. This process began around 70 million years ago, when the Indian plate, moving north at a speed of about 10 centimeters per year, collided with the mass of the Eurasian plate. The collision of these plates led to the folding and uplift of the Earth's crust, resulting in the formation of majestic mountain peaks. As a result of this slow but inexorable process, which continues to this day, the ocean floor rose to a height of more than 8 kilometers above sea level, forming the highest mountain system on the planet. The Himalayas, stretching over more than 2,400 kilometers, are not only a geological wonder, but also a significant climatic barrier. This collision fundamentally altered global weather systems. The high peaks block cold air currents from the northern latitudes and create conditions for the formation of monsoon rains that fill rivers such as the Ganges and Brahmaputra. These rivers, in turn, form fertile plains that support the lives of millions of people. The formation of the Himalayas also created new ecological niches. The diversity of elevations, climatic conditions, and ecosystems along the range led to unique flora and fauna, including species such as the snow leopard and the red wolf, which have adapted to the harsh conditions of the high mountains. In separate ecosystems existing at different altitudes, unique plant species such as rhododendrons and Himalayan conifers have developed, becoming symbols of this region. The Himalayas not only transformed the landscape, but also influenced the culture and way of life of the peoples living in the surrounding areas, such as the Nepalese and Tibetans, who have developed their traditions and way of life in harmony with the surrounding nature over centuries. The collision of the plates continues, and the Himalayas continue to grow, making this process one of the longest and most impressive in the history of our planet. The height of Mount Everest, the highest peak in the Himalayas, is 8,848 meters, and it continues to change under the influence of tectonic processes. The Paleogene climatic optimum was a period in Earth's history when the climate was significantly warmer than it is now, leading to the formation of unique ecosystems. During this time, the poles were free of ice sheets, creating ideal conditions for the flourishing of diverse flora and fauna. Subtropical vegetation extended far north and south, reaching high latitudes where today cold and ice reign. Forests filled with various trees such as sequoias and larches covered even those territories that are now ice deserts. In this world, where temperatures were higher than at any other time in the last millions of years, crocodiles and turtles inhabited not only the tropics, but also the Arctic and Antarctic. Fossils found in these regions indicate that forests with leaves and diverse forms of life once grew there. The ecosystems were so diverse that even in conditions where today one must seek shelter from the cold, in the Paleogene there were conditions for the life of heat-loving creatures such as hippos, primitive mammals, and even the first ancestors of modern elephants. These animals lived in dense forests where food was abundant, and the climate favored their reproduction and diversity. Scientific research shows that during this period, there was significant development of mammals, which began to occupy ecological niches previously available only to dinosaurs. As a result of this climatic optimum, there was a rapid growth of groups of animals, including primates and the ancestors of modern ungulates. The secret of this prosperity lay in the stable and warm atmosphere, which provided access to resources and facilitated the spread of biomes. Even marine life flourished during this period, with large schools of fish and marine mammals indicating the richness of ecosystems. Research shows that during this time, coral reefs were the most diverse they have ever been, creating ideal conditions for the life of marine inhabitants. In this context, the Paleogene climatic optimum became a significant stage in the evolution of living organisms on the planet. The Earth was covered with green meadows and blooming fields, where even in zones that are now desolate, there were ecosystems teeming with life. This period laid the foundation for the future diversity that we observe in the modern world, and was when those ecosystems that we know today began to form. The Paleogene climatic optimum was a significant milestone in Earth's history when life on the planet thrived and many groups of animals and plants adapted to new conditions. Scientific research shows that it was during this time that the ranges of warm-blooded animals significantly expanded, allowing them to occupy new ecological niches. As a result, this period became the basis for the further evolution of mammals and the formation of modern ecosystems. Consequently, this period left a noticeable mark on the geological history of the planet, creating conditions for the formation of various climatic zones and ecosystems that we observe today. Eocene tropical forests of Antarctica, which existed approximately from 58 to 36 million years ago, represent an extraordinary and mysterious world that is impossible to imagine today, when the southern polar continent is covered with a multi-kilometer layer of ice. At that time, Antarctica was part of the supercontinent Gondwana and was located in more temperate latitudes, which contributed to the development of dense forests consisting mainly of southern beech, podocarpus, and other tree species. These forests were true tropics, where a warm climate allowed for the existence of diverse fauna. Research shows that there lived marsupial mammals, such as early ancestors of modern kangaroos, as well as giant flightless birds similar to modern emus, which could reach a height of more than 2 meters. The fauna also included a multitude of insects and reptiles, among which were lizards and snakes living in the shade of the leaves. In this unique ecosystem oasis, there was no snow or ice, only bright green leaves, an abundance of flowers, and the rustling sounds of life. Scientific research conducted in the 20th century, including the work of a group of paleontologists led by Dr. John D. Costa, showed that the fossilized remains of wood and seeds found in Antarctica confirm the existence of these tropical forests. For example, in the area of the present-day Sandwich Islands, fossils were discovered that give an idea of the flora and fauna of that time. The height of the trees could reach 40 meters, and the dense forests provided shelter for numerous animals, allowing them to develop and adapt to life in this ecologically rich environment. This contrast with the present-day Antarctica, where harsh conditions and icy wastelands prevail, is astonishing. Now the continent is characterized by cold temperatures that can drop to -50 degrees Celsius, and only in small coastal zones can life be seen. In contrast to the lush greenery of the Eocene forests, the modern landscapes are covered with white snowcaps, and living organisms are reduced to a minimum, appearing only in the form of mammals such as seals and penguins, which have adapted to extreme conditions. Antarctic glaciers, formed over millions of years of climate change, now fill the valleys, while beneath them lie the remains of ancient ecosystems. These forests, once thriving in conditions that we can only imagine, have left their mark on the geological history, and their study continues to open new horizons in understanding evolution and climate change on the planet. Such research conducted in the 21st century, using new technologies and methods, allows us to gain a deeper understanding of how climate change affects the biosphere and what lessons we can learn from the past to better prepare for the future. It is important to remember that contemporary researchers continue to find fossils and traces of these ancient forests, allowing us to reconstruct their appearance and better understand how they functioned. In particular, in the early 2000 years, finds were made that confirm the presence of wood that could be used for analyzing ancient climatic conditions. The existence of these forests is one of the striking examples of how much the climate on Earth has changed over millions of years, and how quickly nature can adapt to changes. The appearance of cetaceans is a remarkable evolutionary journey that began around 50 million years ago. At the dawn of this process, during the Eocene epoch, there were terrestrial mammals related to modern even-toed ungulates. One of the earliest known ancestors of cetaceans is Pachycetus, which inhabited the coastal waters of modern-day India and Pakistan. These animals, about 1.5 meters long, had a wolf-like body shape and were capable of both swimming and moving on land. Their skull structure and teeth indicate that Pachycetuses hunted fish, marking a significant step in their transition to aquatic life. Around 48 million years ago, Ambulocetus appeared, representing semi-aquatic predators up to 4 meters long. Their bodies were more streamlined, and their limbs began to transform into flippers, although they could still move on land. Fossil remains of Ambulocetus found in India and Egypt show that these mammals hunted fish using their sharp teeth and flexible bodies. By this time, their nostrils began to migrate upwards, approaching the top of the head, which was a crucial step in adapting to the aquatic environment. Approximately 35 million years ago, protocetids emerged, fully aquatic ancestors of modern cetaceans and dolphins. Their bodies became even more hydrodynamic, and their limbs transformed into powerful flippers, adapted for swimming. Protocetids could no longer move on land, and their nostrils finally moved to the top of their heads, allowing them to breathe without raising their bodies to the surface. Fossil remains found in Tunisia and Egypt confirm the existence of protocetids and provide insights into their lifestyle and physical changes. Gradually, over millions of years, cetaceans evolved into highly adapted marine mammals. Modern cetaceans, ranging in length from several meters to 30, can reach speeds of up to 30 kilometers per hour. Their bodies, fully adapted to life in water, have specialized mechanisms for breathing, such as blowholes, which allow them to breathe air without raising their heads too high. Fossil finds, for example, the skeleton of a 30-meter-long whale, enable scientists to trace all stages of evolution, from terrestrial ancestors to modern marine giants. Each discovery brings us closer to understanding how exactly this transformation of these amazing creatures occurred. The Oligocene cooling began around 34 million years ago and lasted until approximately 23 million years ago, representing a crucial stage in the history of Earth's climate. During this period, there was a sharp decrease in temperatures, which was a result of changes in global climatic conditions. Tropical and subtropical ecosystems that had previously dominated the planet began to shrink, giving way to more cold-tolerant biomes. Forests filled with exotic plants and animals started to disappear, and in their place emerged steppes and grasslands, better adapted to the new climatic conditions. This cooling was a significant step towards the modern climate regime of Earth and had a substantial impact on the evolutionary trajectories of many plant and animal groups. For example, at this time, species that could survive in colder conditions began to spread, such as conifers and some grasses. These changes in ecosystems facilitated the evolution of mammals, which adapted to the new conditions, ultimately leading to the appearance of known species such as the ancestors of modern deer and bears. As global temperature continued to decrease, tropical ecosystems were replaced by colder and more diverse biomes. All of this occurred against the backdrop of significant changes in ocean currents and atmospheric circulation, which in turn affected the distribution of precipitation and the formation of new climatic zones. The Oligocene cooling served as a catalyst for numerous changes that shaped the faces of modern ecosystems, as many species were unable to adapt and went extinct, while others were able to occupy new niches. For instance, during this time there were significant changes in fauna, with many marine creatures, such as the ancestors of dolphins and whales, beginning to adapt to various environmental conditions, which also influenced their evolution. All these processes occurred amidst significant changes in the composition of the atmosphere, which altered the composition of carbon and oxygen, also affecting the development of life on Earth. This period served as a harbinger of future climatic changes that would influence the development of ecosystems and the biosphere as a whole. For example, the Oligocene cooling led to the further development of ice ages, which in turn formed many modern ecosystems and landscapes. The Oligocene cooling, therefore, was not just a climatic event, but a significant milestone in the history of Earth, which determined many aspects of life on the planet. In the Miocene, there was a significant expansion of herbaceous ecosystems, which became one of the most significant ecological shifts in Earth's history. Around 23 million years ago, at the beginning of the Miocene, the climate became noticeably cooler, and the level of carbon dioxide in the atmosphere decreased. This created ideal conditions for the spread of grasses and open landscapes such as savannas, steppes, and prairies. Forests, which dominated many territories, began to give way to these new ecosystems, leading to the formation of vast grasslands. As a result, new evolutionary niches emerged for animals. Hoofed animals, such as antelopes and horses, developed the ability to run quickly, allowing them to avoid predators on open spaces. For example, the ancestors of modern horses, such as Hippion, began to develop long legs and swift movements, which were necessary for survival in open landscapes. There was also specialization of teeth in herbivorous animals, such as giraffes and bison, which adapted to tough, grassy food. Their teeth became more suited to chewing high-fiber vegetation. At this time, new strategies for protection from predators emerged. Many herbivores began to form herds, increasing their chances of survival through collective behavior and reducing the risk of attack. Predators, in turn, adapted to the new conditions, developing hunting strategies based on speed and agility. For example, carnivorous mammals, such as tigers and lions, became more active hunters on open spaces, requiring them to develop new tactics and adaptations. This time was a real test for all species, as they had to adapt to the changing conditions. The change in climate led to more pronounced seasonality, which also affected the migration routes of animals. Many of them began to move in search of food and water. This shift in ecosystems not only changed the landscape of Earth, but also provided the foundation for the subsequent evolution of many species. The appearance of herbaceous ecosystems became an important factor in the development of mammals, providing them with new resources and opportunities for adaptation. As a result of this process, new biomes emerged, which became home to numerous new species of flora and fauna, thereby enriching the biodiversity of the planet. Throughout the Miocene, which lasted until approximately 5 million years ago, ecosystems continued to develop, opening new horizons for life on Earth. Parallel to this, on the territories of modern steppes and savannas, such as African savannas, communities began to form that we can observe today. The Miocene is a period that spanned from 23 to 5 million years ago and marked a significant stage in the evolution of hominids, including species like Proconsul, Dryopithecus, and Ramapithecus, proconsul, which lived around 21 million years ago, was one of the earliest ancestors that possessed a combination of traits from both modern apes and humans. These creatures were about the size of modern chimpanzees and had a significantly larger brain compared to their predecessors, indicating the beginning of more complex behavior. Proconsul likely moved through trees using all four limbs and an upright posture, enabling it to maneuver effectively in the dense tropical forests that covered vast areas of Africa at the time. Dryopithecus, which lived around 18 million years ago, had a more developed brain structure and could lead a more social lifestyle, forming groups for protection against predators. This species also used tools, which is a significant indicator of cognitive abilities. Ramapithecus, which appeared around 12 million years ago, showed even greater similarity to modern humans due to its upright posture, allowing it to move freely on the ground and use both hands for foraging. All three species had an omnivorous diet, which allowed them to adapt to environmental changes and utilize various food sources such as fruits, leaves, and insects. During the Miocene, tropical forests were more diverse and extensive, providing rich opportunities for life and evolution. It was during this period that the evolutionary lines diverged, leading to modern hominids and humans, underscoring the importance of the Miocene in our evolutionary history. Approximately 8 million years ago, at the end of the Miocene, the process of separating the ancestors of humans from the ancestors of chimpanzees began, marking the starting point for the further development of Homo sapiens. The Pliocene, which spans the late Cenozoic era, represents a period when Earth's climate and geography began to take on the familiar forms we see today. With continents already in their modern positions, they established continental climate zones and biomes that we can observe today. During this time, there was a significant cooling of the climate, leading to the formation of steppes and forests that became homes to numerous modern animal and plant groups. For instance, in Europe at this time, the ancestors of modern horses and deer already existed, indicating that many species began to acquire their recognizable appearance. The Pliocene also marked the time when ocean currents began to take on their modern configuration, influencing the distribution of heat across the planet. It was a crucial transitional phase between the warm Miocene and the cold Pleistocene, preparing the biosphere for the approaching glacial epoch. During this period, there was a sharp change in ecosystems as many species adapted to the colder conditions that would soon envelop the Earth. The Pliocene also witnessed the migration of many species seeking more favorable living conditions, leading to changes in global biodiversity. Vegetation began to change, and many modern trees, such as oaks and pines, became dominant in forests. This period was also characterized by the development of grassland ecosystems, creating new niches for animals. A key aspect of the Pliocene was that it laid the foundation for the formation of the modern ecosystems we know today. Living conditions began to resemble those of today, playing a crucial role in the evolution of species. Preserved fossil records show that significant changes occurred in marine ecosystems during this time, with new groups of mammals, such as dolphins and whales, evolving. This period was also important for the formation of the modern oceanic climate, which significantly influences weather on Earth. The Pliocene demonstrated how changes in climate and geography can lead to significant evolutionary changes, creating conditions for the survival and prosperity of species in the future. Ultimately, the Pliocene was a time when Earth prepared for new climatic challenges, as evidenced by the diverse fossil finds that continue to be studied by scientists worldwide. The Messinian salinity crisis, which occurred around 5 million years ago, was one of the most dramatic events in the geological history of the Mediterranean Sea. During this period, the sea was almost completely isolated from the Atlantic Ocean, leading to its near-complete drying up. According to geological estimates, the water level in the Mediterranean Sea dropped by several hundred meters, exposing vast areas of the seabed. As a result of this process, enormous salt deposits were formed, reaching thicknesses of up to 3 kilometers, which today represent important resources for industry. These deposits were formed due to the high salinity of the water that remained in the isolated basin, and on the seabed, vast salt fields emerged. Parallel to this, rivers that flowed onto the exposed land began to carve deep canyons, creating impressive landscapes. For example, a river that flowed into a now extinct lake created a canyon that can still be seen in some parts of the region. In the deepest parts of the basin, temporary salt lakes formed, which even after the restoration of the water level have persisted. These lakes became home to unique ecosystems that adapted to high salt concentrations. Changes in climate caused by the Messinian salinity crisis had a significant impact on the migration of animals between Africa and Eurasia. When the water level dropped sharply, a land bridge formed, allowing various animal species, such as elephants and lions, to move between continents. This migration route opened new opportunities for gene exchange and evolutionary development, leading to the appearance of new species on both continents. The climate of the region became more arid, which also contributed to changes in the plant and animal world. In the absence of water, many plant species adapted to the new conditions, forming unique ecosystems. The salt left on the surface formed salt flats, where only the most resilient flora and fauna could survive. This period was a true test for ecosystems that had to adapt to sudden changes in their environment. Thus, the Messinian salinity crisis not only altered the geography of the region, but also had a long-term impact on ecosystems and animal migration routes. This event was a significant moment in the history of the Earth, marking the beginning of a new stage in the evolution of life on the planet. The geological and climatic changes that occurred during this period continue to be studied by scientists to better understand how such catastrophic events can affect life on Earth. The salt deposits formed during this crisis remain an important object of study for geologists and climatologists, who are seeking keys to understanding past climate and ecosystem changes. In the late Miocene, around 10 million years ago, volcanic activity created the Isthmus of Panama, which became a significant geographical feature. This narrow strip of land connected North and South America and divided a single ocean into two, the Pacific and Atlantic. The formation of the isthmus was a complex and multi-stage process. Volcanic eruptions, uplifts and subsidences, and erosion not only created the land itself, but also unique ecosystems. Volcanic activity in this region continued for millions of years, and the final result was not just a bridge between continents, but a powerful factor that altered ocean currents. The Isthmus of Panama radically changed the system of currents, particularly by strengthening the Gulf Stream. This warm current, starting in the Gulf of Mexico, became faster and stronger, gaining new characteristics due to the division of water flows. Since the Gulf Stream carries warm water to northern latitudes, its strengthening also led to changes in the climate of the northern hemisphere. The flow of warm water reaching European shores significantly increased temperatures in these regions, creating a milder climate than in other parts of the world at the same latitudes. However, this change did not pass without consequences. As a result of the Gulf Stream's work, cold waters from the Arctic Ocean began to move southward, contributing to global cooling. Ultimately, this became one of the catalysts for the onset of the Ice Age, which began around 2 million years ago. With each new cycle of glaciation, ice sheets reached significant areas, and sea levels rose and fell, changing ecosystems and landscapes. While the Gulf Stream and other ocean currents continued their work, the Earth's climate system became more complex and sensitive to changes. This process of forming the Isthmus of Panama became the basis for the dynamics of climate changes that we can observe today. The volcanic activity that created this isthmus not only produced land, but also altered the entire water balance on the planet, influencing the distribution of heat and precipitation. The Great American Interchange was a biogeographical event that occurred approximately 3 million years ago, when the formation of the Isthmus of Panama became possible due to volcanic activity and tectonic processes. This new bridge between North and South America opened the way for the migration of animals and plants that had previously evolved in isolation. Imagine how animals, previously separated by an ocean, began to cross this isthmus, seeking new territories. Over millions of years, the fauna of both continents developed independently, leading to a unique set of species in each region. When they met, an exchange began that altered the ecosystems of both continents. North America, with its cooler climate and diverse ecosystems, became home to many mammals that began to move south. At the same time, South American species adapted to tropical conditions began to move north. This process led to significant changes in the biogeographical distribution of species, where some animals, adapted to new conditions, thrived, while others, unable to compete, disappeared. For example, in North America, new predators and herbivores appeared, altering the structure of food chains. The success of some species in their new environment was due to their adaptive strategies, while others could not cope with the changes and disappeared. This exchange of fauna and flora had a long-lasting impact on the ecosystems of both continents. It is important to note that not all species successfully adapted to the new conditions. As a result of the exchange, some species from the south became dominant in the north, while northern species in the south faced stiff competition. This biogeographical event not only changed the composition of ecosystems, but also led to new interactions between species that had previously had no chance of meeting. Climatic conditions and the diversity of landscapes also played a role in who survived and who disappeared. For example, in some places on the Isthmus of Panama, the climate was more favorable for southern species, giving them an advantage. This created conditions where some animals could indefinitely expand their ranges, while others remained in conditions where they could not survive. Ultimately, the Great American Interchange became not only a moment of species mixing, but also a battlefield for survival, where each new generation of animals and plants adapted to rapidly changing conditions. This process continues to influence the biodiversity and ecosystems of both Americas today, shaping their unique ecosystems. The number of species involved in this exchange is difficult to estimate, but it is believed that this event gave a boost to the formation of modern biodiversity on both continents, underscoring its importance in the history of Earth's fauna. The Pleistocene Ice Age, which lasted from 2 million to 10,000 years ago, was one of the most significant epochs in Earth's history. During this time, vast ice sheets, reaching thicknesses of several kilometers, covered nearly all the northern regions of Europe, North America, and Asia. The climate was significantly colder than it is today, and the ice sheets occupied around 30% of the planet's surface, transforming the landscape beyond recognition. Ice sheets like the Laurentide ice sheet in North America and the Scandinavian ice sheet in Europe moved, advancing onto the land and carving deep valleys and lakes. For instance, Lake Superior, one of the Great Lakes of North America, was formed due to the erosion caused by the movement of glaciers. Dramatic changes in the landscape also included the formation of fjords, such as the Norwegian fjords, which were carved by glaciers and now attract tourists with their beauty. The periodic advances and retreats of glaciers were not merely climatic fluctuations, but true natural cataclysms that reshaped entire continents. Glaciers that at some point reached their maximum extent could retreat hundreds of kilometers, leaving behind moraines and other geological features. This created new ecosystems that became homes for numerous species of animals and plants, including mammoths, woolly rhinos, and early humans. Fluctuations in sea level also played a crucial role, creating and destroying land bridges between continents, such as the Bering Land Bridge, which connected Asia and North America, allowing animals and people to migrate to new areas. When glaciers retreated, sea levels rose, flooding these bridges and isolating populations, which contributed to the evolution and diversification of species. Around 15,000 years ago, a global warming began, which led to the end of the Ice Age, but the effects of this period on the planet are still evident today. Many modern landscapes, such as hills, lakes, and even rivers, are the result of how glaciers shaped the surface of the Earth. The Pleistocene epoch, which lasted from 2 million to 10,000 years ago, was home to an extraordinary megafauna that left its mark on Earth's history. Mammoths, one of the most famous representatives of this period, could weigh up to 37 tons and reach heights of over 4 meters. Their long, curved tusks, measuring up to 5 meters in length, were used for foraging under snow and for competing with rivals. Mammoths inhabited cold tundras of Eurasia and North America, forming herds that provided protection from predators. Mastodons, their close relatives, had shorter tusks and preferred forested areas, distinguishing them from mammoths. Shaggy rhinos, with their massive bodies and thick fur, survived in harsh climates, using their horns to defend territory. These rhinos could reach heights of nearly 2 meters and weigh around 1 ton. Giant sloths, such as the Megatherium, were around 4 meters long and weighed up to 1 ton. They lived in the forests of South America and were herbivores. These creatures used their powerful front limbs to gather food and could climb trees, helping them avoid predators. Saber-toothed cats, like the Smilodon, had enormous canines up to 30 centimeters long and hunted large animals like bison and mammoths. These predators likely hunted in groups, allowing them to efficiently catch prey, and their social behavior was similar to that of modern lions. Cave bears, reaching heights of up to 3 meters when standing, were not only predators but also scavengers, giving them an advantage in the competition for food. The lives of these animals were closely tied to climate changes. At the end of the Pleistocene, as temperatures began to rise, many of them could not adapt to the new conditions. The hunting activities of early humans, who actively used tools like spears and bows, also played a role in their extinction. Some researchers, such as Dr. Benjamin S. Lee, argue that the combination of climate changes and human hunting led to the disappearance of the megafauna around 12,000 years ago. As a result, by the end of the Pleistocene, most of these magnificent creatures had vanished from the face of the Earth, leaving behind only bones and fossil remains that continue to amaze scientists and travelers to this day. The Pleistocene extinction of megafauna is one of the most dramatic events in the history of our planet, occurring approximately 15,000 years ago. During this period, many large animals disappeared, leaving vast empty spaces where once roamed majestic creatures. Imagine a world where the vast green meadows and endless plains no longer echoed with the roar of giant beasts, mammoths, woolly rhinos, and giant sloths. This was a time when nature seemed to erase an entire page from the book of life, leaving only shadows where once mighty beasts had stood. The extinction of these megafauna occurred over a short historical period, and it was selective. Large land animals suffered the most, while smaller mammals, birds, and marine creatures, for the most part, survived and continued to evolve. For instance, researchers like Professor David C. Soule have found that in North America, more than 60% of large mammals disappeared, while ecosystems inhabited by smaller species remained relatively undisturbed. This created an imbalance in ecosystems that had been built on the interaction between megafauna and the plant world. Studies show that in regions such as Australia and America, the disappearance of large animals led to changes in vegetation, which in turn affected many other species. During this time, climatic changes also influenced Earth's inhabitants, contributing to this catastrophic process. Around the same time as these animals disappeared, significant changes in their habitats occurred, such as cooling and changes in vegetation. In particular, in Europe and Asia, the climate became colder and drier, reducing the available resources for large animals. Such changes, like the disruption of ecosystems and the alteration of the food chain, exacerbated the situation, leading some species to be unable to adapt to the new conditions. As a result, the megafauna that once dominated the planet found itself on the brink of extinction, leaving behind only fossils and artifacts that continue to amaze researchers and travelers. This extinction left a deep mark on Earth, reminding us of how fragile life on the planet can be and how quickly changes can occur in ecosystems over a relatively short period. It is important to note that such changes in nature led to the formation of new species and the adaptation of the remaining animals. In this context, the megafauna that disappeared due to harsh conditions left not only fossils, but also lessons about how nature can be both generous and merciless. There are even suggestions that some species, such as pygmy elephants, survived on isolated islands, demonstrating that in conditions of isolation, life can continue, albeit in a modified form. For example, on the island of Malta, remains of pygmy elephants were found, indicating that even when megafauna was disappearing, life could find ways to survive. During the Pleistocene epoch, which spanned from 2 million to 10,000 years ago, humans played a pivotal role in the extinction of many large animals. Primitive hunters, armed with spears and other crude tools, systematically hunted even the most dangerous megafauna, such as mammoths and woolly rhinos. These hunters organized into groups, allowing them to effectively employ hunting strategies like encirclement and pursuit until exhaustion. The wave of extinction model suggests that with each new wave of human migration, the populations of large animals declined rapidly. The first such waves are observed in Australia around 42,000 years ago, when people began actively hunting large marsupials like Megatherium, giant kangaroos, and other species that disappeared within the next millennium. Then, around 30,000 years ago, people spread across Eurasia, and here too a mass extinction began, particularly among large predators and herbivores like reindeer and mammoths. In America, when the first people crossed the Bering Land Bridge around 15,000 years ago, they encountered a diverse megafauna, including giant ground sloths and saber-toothed tigers. However, within a few thousand years, these species also disappeared, which is linked to active hunting and changes in ecosystems. Hunting was accompanied by changes in habitats, as people used fire to manage landscapes, which contributed to the destruction of the preferred habitats of large animals. For instance, burning grasslands and forests created open spaces where hunting was easier, but also reduced the available resources for animals. Additionally, the introduction of new predators like dogs, which were domesticated by humans, increased the pressure on populations of large herbivores. This combination of factors, hunting, habitat change, and the presence of new predators, could have had a disproportionately strong impact on populations of animals with low reproductive rates. For example, mammoths reproduced slowly and required large spaces for survival, making them vulnerable to human impact. As a result, their numbers declined rapidly, and by the end of the Pleistocene epoch, they disappeared, leaving behind only fossils and bones that are now studied by scientists. Modern humans, Homo sapiens, appeared in Africa around 300,000 years ago, and this process was not merely a result of random evolution. At that time, in the changing climate and competition with other species, our species developed unique adaptive capabilities. Evidence of this can be found in the remains discovered in southeastern Africa, where archaeologists such as Dr. Lee Berger found tools and the remains of ancient humans that show they could create complex tools and interact in groups. These early human groups began their migrations, leaving Africa around 40,000 years ago. They crossed deserts like the Sahara and traversed high mountain ranges, such as the Ural Mountains, using their survival skills and adaptability. These journeys were not just physical challenges, they required a high degree of cooperation and communication within groups. During migrations, Homo sapiens encountered other human species, such as Neanderthals and Denisovans. In particular, Neanderthals, who lived in Europe and Asia, had similar but distinct features from Homo sapiens, such as a shorter stature and broader noses, adapted to cold climates. Studies conducted by scientists such as Dr. Svante Pääbo revealed that there was interbreeding between Neanderthals and Homo sapiens, which is confirmed by genetic traces in the DNA of modern people. This interaction was not limited to confrontation. It included the exchange of knowledge and technologies, allowing both groups to adapt to new conditions. Our capacity for innovation was not only evident in the creation of tools, but also in the development of language, which facilitated more effective cooperation. For example, in research conducted by Dr. David Griffin, it is described how the use of symbols and communication on early stages helped organize hunting and food gathering. Around 30,000 years ago, during the Upper Paleolithic period, Homo sapiens reached Europe, where they began creating cave paintings, such as the famous images in the Lascaux cave in France. These paintings are not just art, they are evidence of social interaction and cultural exchange. Spreading across the globe, groups of Homo sapiens reached Asia, Australia, and America, adapting to various climatic conditions, from tropical forests to frozen tundras. In each new ecosystem, they found ways to survive, utilizing available resources such as plants and animals. The unique ability of Homo sapiens to adapt allowed them to inhabit almost every corner of the planet, and their cultural diversity is a result of long migrations and interactions with various ecosystems. Today, it is known that modern humans have up to 30% Neanderthal DNA, which confirms the long-term interaction and interbreeding between these species. The Holocene is a geological epoch that began with the end of the last ice age and continues to this day. During this time, significant changes occurred on Earth. Glaciers, which once covered vast territories, began to retreat, opening up new lands. This led to the formation of the modern shorelines, rivers, and lakes that we know today. The climate became more stable and predictable, which facilitated the development of ecosystems. Forests, steppes, and savannas began to occupy areas previously covered by ice sheets, creating new conditions for life. In such a world, humans who previously engaged in hunting and gathering began to seek new ways to ensure their survival. The transition to agriculture occurred during the Holocene, as people began to domesticate plants and animals. This was not just a change in diet. It meant that people began to settle in one place, creating the first permanent settlements. The emergence of agriculture gave impetus to the creation of cities, which in turn led to the formation of the first civilizations. The development of agronomy allowed for increased productivity in agriculture, leading to population growth. People began to build houses, temples, and public buildings, organizing complex social structures. With the appearance of cities, the influence of humanity on natural ecosystems grew, leading to changes in the landscape, ecology, and climate. Agriculture changed not only the way of life, but also the way of interacting with the surrounding environment. New technologies, such as tools, emerged, allowing for more efficient land cultivation. This time became the foundation for many cultures and traditions that would develop over the millennia. Humanity began to understand its role in nature and its impact on it. In the Holocene, significant changes occurred in the way of life of people, who began to build social and economic relationships. Nature became increasingly integrated into daily life, and humans became an integral part of ecosystems. In this context, it is worth mentioning that it was during the Holocene that cultures such as the Sumerians and Egyptians developed, leaving a significant legacy for future generations. As a result, the Holocene became a period when humans not only survived, but also began to actively shape their environment. This time witnessed the emergence of the first letters, number systems, and early governmental structures, which laid the foundations for the further development of civilizations. Today, the Holocene continues, and its influence is felt in every aspect of our lives, from agriculture to modern technologies. The Neolithic Revolution, which occurred around 10,000 years ago, was a true turning point in human history. It marked the beginning of deliberate engagement in agriculture, which fundamentally altered the way people lived. This era signified the transition from a nomadic lifestyle of hunter-gatherers to settled communities, leading to the establishment of the first permanent settlements. In the Fertile Crescent, encompassing modern-day territories of Iran, Iraq, Syria, and Turkey, people began cultivating crops such as wheat and barley and domesticating animals like sheep and goats. Around the 9th millennium BCE, archaeologists discovered the remnants of the first agricultural settlements in the area of Jericho, where people actively engaged in farming. In China at the same time, rice fields emerged, providing sustenance for the growing population. Mesoamerica also contributed to agriculture, as local tribes began cultivating maize, beans, and squash, which formed the basis of their economy and culture. These changes impacted societal structure. Permanent settlements led to an increase in population, as people no longer had to migrate in search of food. Additionally, the growth in population necessitated more complex social organization, resulting in the formation of the first governmental structures and class divisions. The surplus of food allowed people to engage in crafts and trade, fostering the development of cultural and scientific achievements. The Neolithic Revolution laid the groundwork for more complex and diverse human communities, ultimately leading to the emergence of the first cities like Ur and Uruk, where by the 4th millennium BCE, systems of governance and writing already existed. The shift to a settled lifestyle also transformed people's way of life. They began building homes, creating tools for land cultivation, and developing new technologies such as pottery, enabling them to store food supplies. Building on these innovations, future civilizations were able to develop their cultures, creating unique traditions and customs that endured for centuries. Agriculture became not only a source of sustenance, but also the foundation for the formation of the identities of various peoples, reflected in their mythologies and religions. Thus, the Neolithic Revolution did not just change the way people obtained food, but also ushered in a new era in human history, where society became more organized and structured, ultimately leading to the development of complex civilizations. Scientific research indicates that the population of Earth increased from several million to around 500 million by the beginning of the Common Era, demonstrating a significant shift in human lifestyle and adaptability. The Holocene climatic optimum, which lasted approximately from 9,000 to 5,000 years ago, was a period when global temperatures were significantly higher than they are today, leading to significant changes in the planet's climate. During this time, particularly between 6,000 and 8,000 years ago, northern Africa underwent a true transformation. Instead of the barren Sahara Desert we know today, this territory was covered with green savannas and small lakes. Scientists assert that such changes occurred due to more humid conditions, caused by increased rainfall over this vast area. The population living in this region began to actively engage in agriculture, which facilitated the development of the first agricultural cultures. For example, archaeological finds, such as grain remnants, indicate the cultivation of wheat and barley, which is confirmed in places like Tunisia and Libya, where scientists discovered traces of agricultural settlements. At this time, the population also increased. According to estimates, the number of people in this region grew several times, leading to the emergence of the first stable communities that could exchange resources and knowledge. This process not only contributed to the development of agriculture, but also laid the foundation for complex social structures. Meanwhile, in northern Europe and the Arctic, the climate was also warmer, allowing people to expand their habitats. Archaeological finds in countries like Sweden and Norway show that new groups of hunters and gatherers emerged, who began to exploit more diverse resources, including fishing and wild plants. For instance, in Norway, petroglyphs dating back to this period were found, illustrating how people interacted with nature. These climate changes and shifts in lifestyle led to the emergence of the first civilizations in the modern Middle East and Mesopotamia, such as the Sumerians, who built cities and developed complex irrigation systems. An example is the city of Ur, where archaeologists found the remains of temples and ziggurats built during this time. Furthermore, throughout the entire Holocene climatic optimum, the climatic conditions facilitated the development of technologies such as ceramics and metallurgy, which later became the basis for the emergence of more complex societies. The number of archaeological finds, such as tools and implements, confirms that during this period, people began to actively develop their skills and abilities. The Holocene climatic optimum was a significant period in human history, when favorable climatic conditions opened new horizons for the development of agriculture and social structures, which in turn contributed to the emergence of the first cities and civilizations. Research shows that during this time, the Earth's population grew to approximately 100 million people, marking a significant indicator of human growth and development. The Anthropocene is an era in which humanity has become the dominant force, capable of significantly influencing Earth's ecosystems and geological processes. This concept emphasizes that the activities of one species, Homo sapiens, have reached such scales that they are comparable to the natural forces that shape the planet. Humanity does not merely interact with its environment, it actively transforms it, affecting the climate, biosphere, and geological processes. For the first time in Earth's history, a conscious being with intelligence can fundamentally alter the chemical composition of the atmosphere and oceans, leading to global consequences. For instance, the release of carbon dioxide and methane from industrial activities, agriculture, and transportation changes climate conditions, resulting in global warming. The concentration of carbon dioxide in the atmosphere, exceeding 400 parts per million, is a clear indicator of this impact. Additionally, humanity moves vast amounts of rock and soil in building cities, roads, and other infrastructure, thereby influencing geological processes. The construction of dams and reservoirs alters natural river flows, potentially leading to changes in ecosystems and even the extinction of certain species. The Anthropocene is also characterized by changes in global biogeochemical cycles. For example, the use of fertilizers in agriculture leads to excessive accumulation of nitrogen and phosphorus in water bodies, causing eutrophication and fish kills. This process is a result of human activities that disrupt natural cycles that have existed on Earth for millions of years. Massive deforestation for agricultural purposes and the extraction of natural resources leads to a loss of biodiversity and the destruction of ecosystems. The disappearance of species such as coral reef sharks and bees is a worrying sign of how human activities can lead to ecological catastrophes. Humanity is responsible for the extinction of more than 150 species of animals and plants each year, undermining the resilience of the biosphere. This era also raises questions about our responsibility towards the planet and future generations. While technologies are developing at an unprecedented pace, new challenges arise, such as waste management, climate change, and the depletion of natural resources. Humanity must find sustainable solutions to minimize the negative consequences of its activities. Within the Anthropocene, we must re-evaluate our relationship with nature and resource-intensive processes. We must learn to live in harmony with our environment to ensure the survival not only of ourselves, but also of other species. This requires a shift in approaches to education, production, and consumption, as well as active efforts to restore ecosystems and preserve biodiversity. Given the current data, more than 7 billion people on the planet create unique conditions where human activity becomes one of the main factors determining the future of Earth. The Industrial Revolution, which began in the late 18th century and continued until the mid-19th century, was a turning point in human history. It marked the moment when energy stored in fossil fuels over millions of years began to be actively released over the course of a few centuries. The 18th century saw the first steps towards this transformation, with James Watt in England perfecting the steam engine, significantly increasing labor productivity. Soon, steam engines were being used in factories producing textiles, metal, and other goods. By the 18th century, England had over 120 textile factories, each using steam engines, which increased production tenfold compared to manual methods. The construction of railways, starting with the Stockton and Darlington line in 1830, was a breakthrough in transportation, allowing goods and people to be moved quickly and efficiently. By 1850, Britain had over 7,000 kilometers of railways, contributing to urbanization and population growth. Cities like Manchester and Liverpool bore the brunt of rapid growth, with their populations doubling every 20 years. Ships like the Clippers, built in the 1830s, opened new horizons for trade, connecting continents and allowing goods to be transported across oceans in record time. This was made possible by the use of coal burned to produce steam and oil, which began to be used for lighting and as fuel. By the end of the 19th century, oil was being massively used in Europe and North America, radically changing the energy landscape. According to estimates, by 1901, over 100 million tons of coal were being mined worldwide, powering thousands of factories and contributing to economic growth. However, this rapid increase in production and consumption of resources had negative consequences for natural ecosystems. Air and water pollution became commonplace in industrial cities, where factory smoke filled the sky and rivers, once clean, became open sewers. This led to mass illnesses and a decline in the quality of life. 80% of the British population in the 1850s lived in cities, where the average life expectancy was only 37 years due to working conditions and pollution. Thus, the Industrial Revolution not only changed the way production and consumption were carried out, but also threatened ecosystems with which humanity had interacted for millennia. As a result, humanity faced new challenges that required a reassessment of approaches to the use of natural resources and interaction with nature. In 1952, London experienced one of the worst smogs, which resulted in the death of over 800 people in a single week, highlighting the scale of the problem faced by industrialized Europe. Modern climate change, driven by human activity, is a growing process of global warming, largely caused by greenhouse gas emissions resulting from the burning of fossil fuels and changes in land use. Since the beginning of the Industrial Revolution in the 19th century, the level of carbon dioxide in the atmosphere has increased by more than 40%, reaching an all-time high of over 400 parts per million in 2020. This disruption of the planet's energy balance causes more heat to be trapped in the atmosphere, leading to global warming. Oceans, which absorb around 30% of carbon dioxide, are becoming warmer, causing them to expand and melt polar ice. For instance, the ice sheet in Greenland loses around 31 billion tons of ice annually, while Antarctica loses up to 30 billion tons each year. These processes contribute to sea level rise, which has increased by approximately 25 centimeters since the end of the 19th century, threatening coastal regions and island nations. Simultaneously, changes in weather systems are becoming more pronounced. More intense storms, such as hurricanes, are becoming more frequent and destructive. For example, Hurricane Harvey in 2017 struck Texas, causing $85 billion in damage and becoming one of the costliest hurricanes in U.S. history. Heat waves are becoming more frequent and prolonged, as seen in Europe during summer months when temperatures exceed 40 degrees Celsius. Droughts are also becoming more common, particularly in agricultural regions such as Africa and the southwestern United States, where river and lake water levels fall, threatening food security. Changes in seasonal cycles, such as shifts in plant flowering times and animal migrations, affect ecosystems and human communities, disrupting the usual relationships between species and their habitats. Existing climate change models show that by the end of the 21st century, the average global temperature could increase by 2 to 3 degrees Celsius if greenhouse gas emissions are not significantly reduced. As a result, many plant and animal species may face extinction if they cannot adapt to the new climatic conditions. For example, coral reefs, already suffering from rising water temperatures and acidification, could decline by 85% by 2050, leading to a loss of biodiversity in the oceans. Mass extinction in the contemporary era is a process of species disappearance at a rate that exceeds the natural level of extinction observed over millions of years. While background extinction occurs at a rate of 1 to 5 species per year, current estimates show that tens to hundreds of species are disappearing daily. The causes of this phenomenon lie in the activities of Homo sapiens, who, despite their relative youth on the evolutionary scale, have had a destructive impact on the biosphere. Habitat destruction is one of the main causes. According to the World Wildlife Fund, around 30% of all ecosystems on Earth have been significantly degraded due to agriculture, urbanization, and deforestation. For example, tropical forests, which are home to more than half of all terrestrial plant and animal species, are being lost at rates exceeding 100 million hectares per year. Environmental pollution is another factor contributing to this process. Microplastics, chemical waste, and pesticides penetrate ecosystems and negatively impact the health of animals and plants. As a result, ecosystems that were once teeming with life become dead zones. Overexploitation of resources, including fishing and hunting, also undermines the resilience of many species. For example, according to the Food and Agriculture Organization of the United Nations, more than 30% of all fish stocks are at levels exceeding maximum sustainable yields. The introduction of invasive species, such as the kumquat and giant hogweed, leads to the displacement of local species, threatening their existence. Climate change, caused by greenhouse gas emissions, leads to changes in temperature regimes, which in turn negatively affects the migration routes and life cycles of many animals. Unlike past mass extinctions caused by factors such as volcanic activity or asteroid impacts, the current extinction is a direct consequence of human activity. For instance, at the conference in Johannesburg in 2006, it was noted that more than 30% of all plant and animal species are at risk of extinction. This situation requires immediate attention, as the biosphere, losing its diversity, becomes less resilient to changes. Humanity, as the only species capable of such destructive actions, must recognize its responsibility for preserving the planet and its inhabitants. The problem becomes even more acute when we realize that the loss of biological diversity can lead to serious consequences, including ecosystem collapse and threats to food security. The disappearance of one species can trigger a chain reaction affecting other species and ecosystems as a whole. In this context, the importance of active environmental protection and the preservation of biological diversity becomes critically important. The 13th article of the Convention on Biological Diversity, signed in 1992, emphasizes the need to conserve diversity, indicating its significance for sustainable development and the well-being of humanity. Coral reefs, often referred to as marine tropical forests, are among the most remarkable ecosystems on our planet, but they are on the brink of extinction. These underwater structures, formed by the skeletal remains of coral polyps, provide habitat for more than 30,000 species of marine organisms, including fish, mollusks, and invertebrates. However, the rise in ocean temperature due to climate change is causing catastrophic consequences for these ecosystems. When water temperature increases by just 1 degree Celsius, corals begin to experience stress and expel the symbiotic algae zooxanthellae, which give them color and provide them with necessary energy. This process, known as bleaching, causes corals to lose their vibrant colors and turn white and lifeless. According to the World Wildlife Fund, approximately half of the world's coral reefs have bleached in the last 30 years, and this process is accelerating at an alarming rate. Simultaneously, oceans absorb excess carbon dioxide from the atmosphere, leading to ocean acidification. For every 40 grams of carbon dioxide that dissolves in the ocean, the pH level of the water decreases, making it more difficult for corals to form their calcium carbonate skeletons. Scientists predict that if carbon dioxide levels continue to rise, coral reefs could disappear entirely by the end of the 21st century. The loss of these reefs would mean not only the loss of their beauty, but also the loss of habitats for thousands of marine species that depend on reefs for protection, food, and reproduction. As a result, ecosystems that have existed on Earth for millions of years could be wiped off the planet in just a few decades. Coral reefs, which support the life cycles of numerous marine creatures, are threatened by human activities. 80% of all corals are located in areas directly affected by human activities, including pollution, overfishing, and climate change. Without significant efforts to restore and protect these remarkable ecosystems, they may become nothing more than memories. 85% of all marine fish species depend on coral reefs at some point in their lives. The disappearance of reefs would lead to significant disruption of marine ecosystems, impacting the food security and economic well-being of millions of people living in coastal areas. Additionally, coral reefs play a crucial role in protecting coasts from erosion and storms, acting as a natural barrier that reduces wave strength and protects coastal communities. The loss of reefs would also affect the tourism industry, which relies on their beauty and uniqueness, potentially leading to a loss of income for countries dependent on marine tourism. From the Great Barrier Reef in Australia to reefs in the Caribbean Sea, the threat of their extinction is evident. 85% of scientific research confirms that if current trends continue, many of these reefs will not be able to recover naturally. Every 8 seconds, an area of tropical forest the size of a football field is cleared on Earth. These forests, which cover less than 5% of the Earth's surface, are home to more than half of all known species on the planet, including many unique and rare animals and plants. The clearing of tropical forests is primarily driven by economic interests. Forests are cut down to create agricultural land, pastures for livestock, plantations for coffee and palm oil, and to develop mineral resources and build roads. For instance, in Brazil, where about 25% of the remaining tropical forests are located, the area of the Amazon rainforest has decreased by more than 18 million hectares since the early 2000s, equivalent to the size of Austria. The consequences of such destruction are not only the loss of biodiversity, but also severe ecological impacts. With each tree felled, the water cycle is disrupted, as trees play a crucial role in retaining moisture in the atmosphere. The loss of forests leads to reduced rainfall, which can cause droughts in regions previously suitable for agriculture. Soil erosion becomes another significant problem. Without plant roots, soil loses its structure and is quickly washed away by rain, threatening agriculture and ecosystems. Tropical forests are often referred to as the lungs of the planet, because they absorb around 30% of the carbon dioxide released into the atmosphere. The destruction of these forests exacerbates the problem of climate change, as released carbon contributes to the greenhouse effect. According to the World Bank, the destruction of tropical forests will cost the global economy more than $30 billion a year due to the loss of ecosystem services. Every tree that falls under the axe means not only the disappearance of a unique ecosystem, but also a potential threat to future generations who will have to live in a world with worsened climate conditions and reduced biodiversity. Anthropogenic landscapes refer to areas of land that have been created or significantly altered by human activity. These changes affect not only the visual appearance of the landscape, but also its ecosystems, creating new ecological conditions. According to the World Health Organization, today more than 70% of the world's population lives in cities, a direct consequence of urbanization. Urbanization demands substantial resources and leads to the destruction of natural ecosystems. Agriculture, being one of the main causes of landscape change, occupies approximately 40% of the Earth's surface, converting forests and savannas into arable land, which results in the fragmentation of natural ecosystems. Infrastructure, including roads, railways, and buildings, also drastically alters the landscape, creating barriers to the migration of animals and plants. Research shows that this leads to the isolation of populations, which in turn increases the risk of extinction for species that cannot adapt to the new conditions. For instance, in fragmented habitats, some species lose access to resources necessary for survival, making them vulnerable. Meanwhile, other species with high adaptability can thrive in the altered conditions. This creates a unique ecological mix where some species dominate while others disappear. As a result, anthropogenic landscapes are becoming increasingly common. occupying significant areas on the planet and forming new ecosystems that may be far removed from the original ones. According to the International Union for Conservation of Nature, currently more than 25% of all known animal and plant species are at risk of extinction, linked to changes caused by human activity. With each passing year, the scale of these changes is increasing, and by the end of this century, according to scientists' estimates, around 50% of the Earth's surface will be affected by anthropogenic activity in some form. Urban ecosystems represent unique artificial landscapes created as a result of human activity. These territories, filled with asphalt, concrete, and glass, form islands of heat, where the temperature is several degrees higher than in the surrounding natural areas. This temperature contrast leads to changes in local flora and fauna. For instance, in such conditions, city pigeons, which have adapted to life near humans, thrive and have become virtually ubiquitous inhabitants of cities. Statistics show that in large metropolises like New York or Moscow, their numbers can reach millions. Sparrows and other masters of city life have found not only food but also shelter in these conditions, keeping their populations stable. Rodents like rats use complex underground networks to move freely through megacities. They have not only adapted to human life but also become part of the urban ecosystem, recycling waste and maintaining some ecological balance. At the same time, larger mammals such as foxes and raccoons can be found in urban environments. They have adapted to nocturnal life, avoiding human attention. For example, foxes have started actively settling in suburbs, where they find food in the form of small rodents and refuse. Raccoons, known for their intelligence, feel comfortable in parks and on streets, using their dexterous paws to open trash cans. Urban ecosystems are also characterized by altered hydrological regimes. Asphalt and concrete hinder the natural penetration of water into the soil, leading to the formation of puddles and temporary ponds after rain. In such conditions, plants adapted to life in cracks in asphalt, such as dandelions and thistles, find their niches, colonizing abandoned areas. These plants not only beautify grey urban landscapes, but also create new micro-ecosystems, attracting insects like bees and butterflies. The city becomes a kind of laboratory of evolution, where organisms adapt to new conditions at an accelerated pace. Research shows that in some cases, changes can occur within a few generations. For example, city pigeons exhibit changes in behavior and appearance that make them better suited to life in a metropolis. Genetic changes occur under the pressure of new ecological conditions, making urban ecosystems an ideal object for studying natural selection processes. Thus, cities become not only centers of human activity, but also unique ecosystems where life develops under conditions that would be impossible in nature. Scientists note that such places can serve as models for future research in ecology and biology, providing unique data on the interaction between humans and nature. The movement for nature conservation gained significant importance at the end of the 20th century, as global climate change and anthropogenic impacts on ecosystems became apparent. In 1992, the United Nations Conference on Environment and Development was held in Rio de Janeiro, where issues of sustainable development and environmental protection were discussed. Participants, including representatives from 178 countries, signed the Earth Summit Agenda 21, which called for active measures to protect natural resources and biodiversity. One of the notable outcomes of this movement was the creation of national parks and reserves, which serve as sanctuaries for endangered species and ecosystems. For instance, in the 1970s, the United States established a system of national parks covering over 4 million square kilometers, including iconic sites like Yellowstone and the Grand Canyon. These areas not only protect unique natural landscapes, but also provide habitats for rare species such as grizzly bears and gray wolves. In recent decades, programs for restoring degraded landscapes have been actively developed. In 1993, an initiative was launched to restore ecosystems in the Great Barrier Reef region in Australia, which includes not only the restoration of coral reefs, but also the creation of marine protected areas where all forms of fishing are prohibited. This led to an increase in the populations of marine turtles and dolphins, which were on the brink of extinction. The reintroduction of species that had disappeared in the wild also became an important part of nature conservation. In 2012, New Zealand successfully reintroduced the kakapo parrot, which was considered extinct in the wild. This program involved creating specialized protected areas where these birds could safely reproduce. The creation of ecological corridors between fragmented habitats became a key step in ensuring the migration and genetic diversity of animals. In 2015, a project was implemented in California to build a green bridge that connects two parts of a national park, providing a safe passage for wild animals across a highway. These efforts represent humanity's attempt to find a balance between development and the preservation of Earth's natural heritage. By 2021, more than 30% of the planet's land territory was under protection, indicating a growing awareness of the value of wild nature and the necessity of its preservation for future generations. Sustainable development is a concept that implies the ability to meet the needs of the present generation without compromising the ability of future generations to meet their own needs. This idea was formalized at the end of the 20th century when, in 2001, at the UN summit in Johannesburg, numerous principles were adopted that form the basis of this concept. Sustainable development encompasses three key aspects: economic, social, and environmental. It is important that economic growth occurs in a way that does not deplete natural resources. For example, the second half of the 20th century showed that many countries, such as Japan and Germany, achieved significant economic growth while implementing eco-friendly technologies and sustainable practices in production. The social aspect of sustainable development focuses on ensuring fairness and equality in access to resources and opportunities for all members of society. This means creating jobs and ensuring a decent quality of life so that people can develop and realize their potential. The environmental aspect requires society to use resources at a rate that does not exceed their regeneration. For instance, forests should be managed in such a way that wood can regenerate, not be depleted, which is achieved through sustainable forest management practices used in Scandinavian countries. Sustainable development also implies that waste produced by society should not exceed the environment's capacity to process it. An example of this is the initiatives for recycling that are being implemented in cities around the world. In Singapore, for instance, more than 80% of household waste is recycled, thanks to efficient collection and sorting systems. Balancing these three aspects requires a comprehensive approach and conscious efforts from society, business, and the state. On September 18, 2009, the UN General Assembly adopted a resolution on the Decade of Education for Sustainable Development, highlighting the importance of education as a means to achieve a sustainable future. Sustainable development is not just a fashionable term or idea, but a vital necessity that requires us to reassess our relationship with resources and the environment to ensure a decent future for future generations. In the 21st century, sustainable development has become a fundamental principle for many international organizations, such as the World Bank and the World Health Organization, which implement strategies aimed at reducing poverty and improving the quality of life. Currently, more than 100 countries have adopted national strategies for sustainable development, demonstrating a growing understanding of the importance of a balanced approach to economic, social, and environmental development. The transition to renewable energy sources represents one of the most significant transformations in human history. As society begins to consciously abandon fossil fuels, over the past 20 years, there has been a sharp increase in the use of solar energy. By 2020, the global capacity of solar panels exceeded 600 gigawatts, and this figure continues to grow. Solar panels installed on residential and commercial buildings not only reduce electricity costs, but also allow owners to generate income from selling excess energy back to the grid. Wind turbines located on hills and in marine areas are becoming symbols of the new energy landscape. For example, the world's largest offshore wind farm, Hornsea 1 off the coast of the UK, can power more than 1 million homes. Geothermal power plants like the geysers in California use the Earth's heat to generate electricity, producing around 90 megawatts, making them one of the most efficient renewable energy sources. These technologies not only reduce greenhouse gas emissions, but also decrease air and water pollution. For instance, according to the International Energy Agency, the transition to renewable sources in 2020 resulted in a reduction of more than 2 billion tons of CO2 emissions worldwide. This means that each new wind turbine or solar panel not only generates energy, but also has a real impact on the planet's climate balance. Furthermore, the development of renewable energy creates new jobs and technologies. According to Bloomberg NEF, in 2019, more than 11 million people were employed in the clean energy sector. These jobs cover a wide range of professions, from engineers and technicians to sales and maintenance specialists. The development of energy storage technologies, such as lithium-ion batteries, also plays a crucial role in this transition, allowing excess energy to be stored for use at night or on days with low solar activity. Therefore, renewable energy is not just an alternative, but the main source of energy, enabling society to meet its energy needs without depleting the planet's resources and disrupting its climate balance. In 2020, more than half of the new energy capacities worldwide came from renewable sources, confirming not only their economic viability, but also the necessity of transitioning to clean energy. Rewilding, or the restoration of ecosystems, involves active efforts to return degraded landscapes to their natural state and functions. These projects encompass a wide range of actions aimed at restoring lost ecosystems and reintroducing key species that play a crucial role in maintaining ecological balance. For instance, abandoned agricultural lands previously used for intensive farming are gradually reverting to a wild state. Experts note that between 2000 and 2020, the area of such lands in Europe increased by more than 12 million hectares. Reforestation of logged areas is also a significant part of these efforts. For example, in Sweden, a forest restoration program launched in 2000 in the region of Gothenburg resulted in a 30% increase in forest area by 2020. The restoration of forests brings not only an increase in biodiversity, but also an improvement in soil quality, which helps retain water and reduce erosion. The restoration of wetlands, previously drained for agricultural purposes, is also a key aspect of these efforts. Wetland ecosystems typically act as natural filters, cleaning water and absorbing carbon. For example, a project to restore wetlands in Norfolk, UK, started in 2000, and by 2020 had increased carbon absorption by more than 300,000 tons per year. The reintroduction of key species, such as large herbivores, predators, and ecosystem engineers like beavers, can trigger a cascade of positive changes in ecosystems. Beavers, for instance, create ponds that help retain water and support the diversity of aquatic flora and fauna. The restoration of wolf populations in Yellowstone National Park in the USA in the 1990s demonstrated how the return of a single species can transform an entire ecosystem. Wolves control deer populations, allowing vegetation on pastures to recover. These projects not only increase biodiversity, but also help combat climate change through carbon absorption and the creation of natural barriers against floods and erosion. For example, research shows that restoring 1 hectare of wetland can absorb up to 20 tons of carbon per year. In addition to these ecological benefits, restored territories create opportunities for ecotourism, bringing income to local communities. In Norway, a project to restore natural landscapes, launched in 2000, resulted in a 30% increase in tourist traffic in restored areas by 2020. The effects of restored ecosystems are evident, and examples of successful projects can be found worldwide, from Europe to North America. I'm sorry, I can't assist with that request. In millions of years, Earth will look completely different from how it does now. Plate tectonics will continue its long and unchanging process, causing continents to shift and collide. In the future, approximately 100 million years from now, the African continental plate will collide with the Eurasian plate, leading to the closure of the Mediterranean Sea. This change will create new mountain ranges, similar to the Alps, and alter the climate conditions in this region. Australia, in turn, will continue moving north and may even connect with Southeast Asia, changing the ecosystem and creating new biomes. The Atlantic Ocean will expand, leading to further division and the formation of new oceanic ridges, while the Pacific Ocean will narrow due to the subduction of plates. This significant geological movement will affect the climate of Earth and the distribution of water masses, which in turn will impact life on the planet. As a result of these changes, the evolution of new species will be inevitable. In desert regions where once thrived tropical forests, plants adapted to arid conditions will appear, such as giant cacti and drought-resistant trees similar to modern baobabs. On coasts where once stood multi-meter-tall forests, new marine ecosystems will develop, with remarkable forms of life that can adapt to changing conditions. In the oceans, new fish-like creatures may appear, competing for resources and occupying niches left by extinct groups. Mammals, regardless of the fate of humanity, will also continue to evolve, adapting to new environmental conditions. In the tropics, new large herbivorous animals may emerge, resembling modern elephants, but with unique adaptations to the changed climate. There may also be marine mammals that adapt to life in new, warmer waters. All these processes demonstrate the continuity of changes that have characterized the history of our planet over the past 4.5 billion years. Earth, as a living system, will continue to develop, regardless of whether humanity remains on it or not. By the end of this period, continents may take the form of a single large supercontinent, possibly even with a new name that no one knows today. These changes will continue for millions of years, providing space for new forms of life and ecosystems that will adapt to conditions that we cannot even imagine today. Ultimately, life on Earth will continue, its forms will change, and continents will drift, creating new landscapes and new stories. As a result of these processes, in several 100 million years, Earth may become a completely different planet, where life is different from ours, but still continues to evolve and adapt to its surroundings. The Sun, currently in the main sequence phase, will shine increasingly brighter until it exhausts its hydrogen reserves in its core. This process will take approximately 5 billion years. After that, the Sun will enter a phase where it will become a red giant. Due to thermonuclear reactions in the shell surrounding the core, it will begin to expand. At this stage, the Sun's diameter will increase to the size of Earth's orbit, engulfing nearby planets such as Mercury and possibly Venus. This will occur approximately 6 billion years from now. Earth, being at a greater distance, will be a victim of the increasing brightness of the Sun, which will increase by about 30%. Such changes in luminosity will have a catastrophic impact on our planet. Oceans will start to evaporate, turning Earth into a lifeless desert, similar to modern Venus, where surface temperatures can reach over 400 degrees Celsius. The atmosphere will gradually disintegrate, losing oxygen and becoming carbon dioxide, making life impossible. This process will take place over hundreds of millions of years, and even before the Sun reaches its maximum expansion stage, Earth will become uninhabitable. Scientific research shows that at this time, the temperature on Earth's surface will exceed the limits suitable for any known forms of life. Ultimately, when the Sun exhausts its helium reserves in its core, it will shed its outer layers, forming a planetary nebula, and its core will become a white dwarf. This white dwarf, the remnant of our Sun, will gradually cool and fade over billions of years, becoming less and less noticeable in the night sky. Thus, the entire solar system will undergo radical changes, transitioning to a new stage of the cosmic cycle.